drop it without creating the ice structure inside the crystals. And they claim that they could collect data like that and reduce the radiation damage. I haven't tried that yet.
I'll give it a go.
Yeah, it would be interesting to see that, because that would extend the lifetime quite a bit, I think.
Yeah.
So this morning we'll be talking mostly about just the software suite that goes along with the hardware. So and I'm going to go through this relatively fast probably, and you won't pick up a lot of it, but I just want to give you an introduction to it. So one of the things we like to do is to do some tutorials remotely. So if you get to the point where you have questions about the software or even problematic data where you're having trouble indexing something, contact me and we can do a WebEx section and I can go through and sort of explain what the program's doing and even help with some of the data that you're trying to work with. So that's worked well with us in the past where we can just set up a quick remote session and then I can share my desktop or I can follow you when you're trying to do data collection and I can give you some advice. So that's what I would recommend, that today you won't pull a lot out of this. You'll get to see what the software, how the software is laid out, what it can do. And then you'll get to work with the hardware a little bit, but you really don't have a lot of questions until you actually start using the instrument. And so when you start doing that, you'll have more questions or issues, and then just contact me, and obviously Joel will be able to help you as well.
And for the afternoon session, it's going to be kind of hands-on, but we can't get everybody at one time, so we've broken it up into 4 sessions, and I've got sign-up sheets over here. So if you sign up for one of the sessions, it'll be 2 this afternoon and tomorrow.
And basically for the hardware sessions, it's just an idea of how you would actually put a sample on, align it in the beam, and then screen your crystal, start a data collection.
Just sort of an introduction. I'll actually go through it with you before you get solo. So you don't have to remember everything from the day.
And it's like anything else. It's when you haven't done it before, you're a little apprehensive about it. But once you've used it a couple times, it's pretty straightforward to use. So when we go in there, you'll see the enclosure. It's all radiation safe, so you can't open the main beam with the enclosure open. So it's the enclosure itself is self-contained, so there's no radiation coming out. So the beam you have is actually quite hot, and I've got a spec on here for the number, but it's probably the hottest source that you have in a home lab.
Unfortunately, that enclosure is almost impossible to open up the door and have the shutters not closed or something like that. It's very, very safe.
Yeah, there's machine directors out of Europe that you can't even move the goniometer except for the phi motor with the doors open. So they're trying to make it so you can't hurt yourself. And the enclosure itself is pretty thick metal. So even at high energy, you wouldn't penetrate it for the most part. So. Did anybody not get a? This is my business card, and I'll have my contact information up here. Should we start?
Yeah, let's. You might as well go ahead and get started.
Okay, my name is Matt Benning. I'm the application scientist for the biological product lines for Bruker. So I'm the person that you would talk to on the technical basis for just using the system in general, and then we have in-house service engineers as well. So the person that you would talk to mostly is someone called Todd Larson. He actually worked with me at the University of Wisconsin. Todd has got a PhD in biochemistry and worked at UW for a while and then came work with us. My background is that I was at the University of Wisconsin for 12 years. I worked with Hazel Holden and Ivan Ramet in the structural biology lab at Wisconsin. And then I moved to Bruker, and I've been there for about 18 years now. So my background is in chemical crystallography, and then when I went to Wisconsin, I started doing structural biology back in the 80s. So I've been doing it for quite a while. This is just my contact information, so you can email me if you have questions or problems. You can call my cell. If you're desperate on the weekend and can't get a hold of somebody, if I see somebody calling, I will usually answer. So if you need help, I'll give it to you. But for sure, email. I'll get back to you if you have a question or a problem. And that's on my business card. So the system you have is called the D8 Venture. So at the first part of my talk today, I'll go through just the hardware, just some brief information about what the hardware is, and then I'll go through the software, different components of the software that you would use when you were doing both data collection and data reduction. So the D8 Venture can have multiple sources, but you have what's called the METALJET, and it's a unique X-ray source that was started being developed back in the 2000s and by a company called Exilum out of Sweden. And I'll talk a little bit about what the METALJET is. It's a different way of generating X-rays that, as opposed to the classical, where you have a solid target and such as a rotating anode or a sealed tube source. We design our own optics, so they're called the Helios optics. We have our company called Incotec in Germany that makes optics for both home labs and beam lines. They also make our X-ray tubes for our sealed tube sources. You have a photon 2 CMOS detector, and I'll explain what that is. Some of you are familiar with the Pilatus or Dectris detectors at the beam lines. It's a similar technology, but a little different way of detection, and I'll talk about that. The detector for a home lab system for a sensor-based detector is actually quite large. It's about 100 by 140 millimeters squared. So it's got a fairly large active area, and the point spread function is pretty good. So for instance, on your system, a lysozyme that has a unit cell length of about 80 angstroms, I could resolve at, say, 40 or 45 millimeters. And I'll give you some idea when we're in the lab of kind of what distances you would have to be at to resolve the spots for different unit cells. You have a kappa goinostat on this system, which is some of you are probably not familiar with. They're having them more and more at the beam lines these days, but in years past, most of the goniometers were single spindle rotations. And the kappa has some unique features to it that really aid in data collection. And the whole system itself is OPCO managed, which means that all the hardware has a radio frequency tag. And so when you take something off or put something on, the program automatically knows something's been removed or added. And so then it creates a hardware map so that the system knows where it can go, what angles it can move to. So it's what we call a collision map. So it prevents the angles, anything of the hardware from running into each other. And so you'll see it when you put a crystal on and you move the crystal to a specific set of angles. It'll move pretty fast. And so it looks like everything's going every which way, but the software knows where to go. The hardware has a CAD. Each one of the components are CAD enhanced into the map, and so then it knows where to go, so you don't have to worry. And the software prevents you, based on the collision map, from going to an angle that's not allowed. And I'll show you the 3D viewer that it has with it as live. So if I were to pull the beam stop, for instance, the beam stop would disappear from the collision map. So the METALJET itself is a little different way of generating X-rays. So the standard way that we've used for decades is that you take a solid target, you hit it with an electron beam, and that generates X-rays at an energy based on what the material is that you're using for the target. The METALJET's a little different. What it uses is a stream of liquid gallium, liquid metal. So the old problems with a solid target is that the more power load you put on it, the more heat you're generated, the more you can destroy the solid target. And at some point, you just end up melting the target. So you're limited to the power load that you can put on a standard rotating anode, for instance. With the METALJET, the target's already melted, so you don't have to worry about that you're going to destroy the target. And then that gives you a way to increase the power loading, increase the intensity. Your intensity is going to be around 3.5 to 4 times 10 to the 11th photons per second per millimeter squared. So that's getting close to some beam lines, not necessarily third generation ID lines, but certainly the bending magnet lines. So it's pretty intense beam. The wavelength is a little shorter than typically used in home lamp systems. So typically the target is copper, and so the wavelength is about 1.54 angstroms. So gallium has a fluorescence edge around 1.34 angstroms, so that will be your wavelength for this, so it's a little higher energy. The beam size is actually quite small, so it's actually focused fairly tightly for an in-house source. And it's a Gaussian curve, so it's fairly strongly peaked. So most of the counts fall within the full width half max of the profile. And so that's what we usually quote as the beam size. So the beam size is about 70 to 80 microns. So if you throw on a 400 micron crystal, you're really not going to gain anything by that. And so this machine is basically designed for smaller crystals. Usually the scaling, you can use larger crystals, and that's not a problem. The scaling will mitigate any systematic errors that arise because of that. But it is really geared towards having smaller crystals because that's where structural biology has gone over the years, and it's harder and harder to get crystals of some of the complexes and some of the types of targets you're working with. So 150 microns or less is probably a good target range for a lot of the samples you shoot. And a lot of times it'll be 100. It could be 200 microns in one dimension, and the other two dimensions can be very short. So, and that's fine. And the scaling, our scaling package does a really good job of, like I said, mitigating any of the differences in crystal volume as you do your data collection. One of the reasons that we are geared towards this type of source is that it's air-cooled. It doesn't require water cooling, external water cooling. There is an internal water loop. And so there's no chiller that you have to have like you have to have with rotating anodes. There's no really any moving parts, so there's no ferrophilitic vacuum seals, there's no bearings to change, so it's actually quite nice as far as maintenance goes. The one thing it does do is it constantly recalibrates the electron beam. So the electron beam hits the target to generate your X-rays. And you may see that. So you may see a message pop up if you go to collect data and it's going to go past the calibration time. It'll come back and say, do you want me to recalibrate now? And so it will automatically recalibrate the system for you if it's going to go past its scheduled calibration time. I would recommend doing that. It only takes like 2 or 3 minutes to do the recalibration. Otherwise, it will collect, it'll stop, recalibrate, and then continue the data collection. So this is just sort of an idea of what the METALJET is doing. So instead of a solid target, we're using a liquid target. And so we get a stream coming down, and that's what the E-beam strikes to generate your X-rays. So what's really nice about that, with a solid target, as you hit it with the E-beam, you start to get roughening of the surface of the target. And you start to also get tungsten depositing on the target from the filament that's evaporating. So if you ever looked inside a rotating atom, you look, it's kind of a bluish silver color over time, and that's a tungsten coming back off the filament as it evaporates. That's generating the electron beam. And so because you don't have a solid target, you never have any roughening. You actually keep the intensity of the METALJET stays the same pretty much through its lifetime. You don't have to polish a target over time. And that's really nice, that the target is actually regenerating itself. And so that was one of the other advantages that we had when looking at the system. And so it's pretty simple design inside. So it's just got a gallium, there's a pool of gallium at the bottom that's IR heated, and gallium is liquid at room temperature, but the viscosity is pretty high. So we heat it up a little bit just to make the gallium flow a little bit better. And so there's a stream that comes down, and then here's your electron gun here. It's not a filament. It actually uses a lanthanum hexaboride crystal for generating X-ray or electrons. And so one nice thing about this is that you get to a point where you need to do a cathode change just like you would do on a standard rotating anode, but you don't have a complete failure. What you have, like you would have a filament would break and then you'd have to change a filament. What ends up happening is that eventually you can't focus the beam as well. And so you can still use the system. So what I'm referring to then is that there's no sudden failure of the system. You can keep using it even though it needs a cathode change, which is nice because if you're trying to get ready for a beamline trip and the filament would break, for instance, you'd have to repair it, so you'd have to stop. Here you can just deal with a little less intensity, a little bigger spot size. There's a focusing coil for the electron beam, turbomolecular pump that's inside to create the vacuum, and that's pretty much it. And then your optic is right here, so there isn't any moving parts inside, which is nice. There are consumables that you have to change, like the cathode. There's a exit window that you have to replace routinely, and there's a nozzle for the stream that has to be replaced every so often. But for the most part, there aren't a lot of things that have to be repaired. So that's the METALJET. That's your source. So on the detector side, you have what's called the Photon 2, which is a CMOS detector. So CMOS sensors are now what's used in almost any imaging device. CCDs were used for years, back in the 90s and 2000s, but now CMOS sensors have taken over, and they're in your cameras. They're everywhere. And the reason is that lithography has gotten a lot better for designing these sensors. And so a CMOS sensor has some pretty good advantages over a CCD. And so this was the first CPAD detector. A CPAD is a charge integrating pixel array detector, and I'll explain what that is. So the active area, as I mentioned, is 100 by 140 millimeters squared. This is also air-cooled, so the whole system doesn't require an external chilling, which is unique for X-ray systems. It's a highly sensitive detector. It's a single sensor, so you don't have any gaps like you would have with a high pad, and then I'll explain what that is in a second. And we use an adaptive oversampling method to reduce the noise level, and I'll talk a little bit about that. That's a way to improve the precision of your measurements. It does a shutterless data collection, so like CMOS, you can expose and read out at the same time, so you never have to stop your crystal while you're collecting data. So with a CCD detector, what you'd have to do is rotate your sample, stop, read the detector, clear it, and then go back, speed up, hit that spot, and then go to the next image. Where with the CMOS, you can read and expose at the same time, so you just keep continuously spin your crystal and just keep writing out frames. That's really nice. Cuts out some mechanical error due to the shutter alignment. And the longest exposure time you can do on this detector is through software is about 10 minutes. But my guess is you'll never go past 1 or 2 minutes, because if you can't see anything in 1 or 2 minutes, or you're not going to do any better after that, because the sensitivity of the detector is pretty high. So you're not going to gain much by, you're doing 2, and I'm going to try to double it, go to 4. I'm not going to see much more. So the CMOS detectors are something that developed in the last, really have boomed in the last maybe decade and a half. And the reason is, as I just mentioned, you can actually do shutterless data collection. You can read and expose at the same time. You have very high frame rates. So you write out images very quickly. The chip or sensor can be read very quickly. You have high spatial resolution, so that means you've got high, you can resolve spots really well on the detector. Most of them have photon counting capabilities. Yours has capabilities that are close to that, but is not a true photon counter. And I'll explain that in a second. And they have very low power requirements. So CMOS sensors actually run on lower power than CCDs, so the electronics are more stable. So there's 2 types. So the ones you're probably more familiar with are the Dectris detectors, and they're what's called a hybrid pixel array, or HPAD. And so it does direct conversion of X-rays to electrons. And so what you see here is you have a wafer. The X-rays come in, they strike the wafer, they generate electrons and electron holes, and that's your charge that builds up and then is transferred to a CMOS sensor. So that's how the Dectris detectors work. It's a direct conversion of X-ray to electrons, and that's a signal that you measure. Our detector is a charge integrating pixel array. It's an indirect conversion. So X-ray comes in, hits a scintillator, it's a phosphor. It's not a storage phosphor, it's a quick release. And so you generate light, and that light then, in turn, through the photoelectric effect, generates electrons, or a signal in the sensor. So it's a little different way of actually using the CMOS sensor to detect your signal coming in, but it still has the same CMOS technology. So why are people using charge integrating pixel arrays? So they're actually easier to measure strong and weak reflections at the same time. And so at the X-Feld lines, for instance, they've started to go to the charge integrating pixel arrays rather than the true photon counters. So you'll see a lot of CPAD technology being developed at the 4th generation beam lines. So what's really nice about the CPAD is that it is a massively parallel output. And so it reads very fast, so you can get high frame rates, just like you can with the HPADs. But you can measure the charge fully, so you get a full integrated charge as opposed to applying a threshold that you do in the HPADs to generate a signal. The noise of the readout electronics of the new CMOS sensors have really gotten good, and the noise levels really dropped, and that's what's made these detectors, we're able to use those as photon counters these days. And our latest generation of the detector is actually has photon counting statistics, or meets photon counting statistics. And the other really cool thing about this type of CMOS detector is that it has an effective gain that's variable. So the sensor can detect when a strong signal can come in and it can switch to a dynamic mode. So instead of going to a very sensitive read mode where the full well is lower, so it overloads the reflections, it switches and goes to a higher full well mode. Or if the signal coming in is very weak, then it'll switch to a dynamic mode. So that's a great way to measure both weak and strong reflections at the same time. So for your detector, then you have an integrating detector. You will be upgrading to a detector that's got what we call sensitive and dynamic mode. So it has that variable gain. And it's more in how we handle the data coming in rather than the detector itself. So that will be an upgrade you'll be getting this summer. Right? So that increases the sensitivity of the detector substantially. We have an non-destructive read mode, which I'll talk about in a second, and then you have the frame rate, which is 70 hertz, which is, we're reading out the detector very quickly. So you're not going to be collecting on the same time scale you would at the beam lines, right? So you're not going to be doing your data collections in less than 5 minutes or 3 minutes typically. So to have a very high frame rate really doesn't help you in-house unless you use it in another way, and that's what we do. So we take advantage of the frame rate to increase the precision of the measurement. So if you think of a movie that's just a collection of stills, The final image then is that collection of stills that gives you your actual movie. And so that's what we're doing through a method that's called adaptive oversampling. So what we do is we take the true image in a series of very short exposures. And so by doing that, we can get a better averaged out signal for that one frame. So say, for instance, we do 70 hertz, so we do 70 frames in 1 second. So as a result, then you get a much better measurement of what that pixel value is averaged over that time frame. And so this gives you a higher precision for your intensities. So what the program can do is both non-destructive and destructive read, or the detector can do. So non-destructive reads and exposes at the same time, and then at some point very quickly it will read out the sensor, reset it, and go on. So you get 13 non-destructive, 1 destructive read. And so what we do then is use these sort of wedges to determine what the true counts are for a particular exposure time. So each frame is a subset of a series of these non-destructive and destructive reads. And so this helps us to measure on a very short time scale what the pixel counts are. So that basically eliminates thermal noise in or dark current in the chip, because you're measuring very short exposures rather than very long exposures. And so each frame is just a series of these non-destructive and destructive reads. And so you can vary this depending on the exposure time. So with very short exposures, you're really not worried about the dark current, so it does less of these and extends the dynamic range with the very strong reflections. On your weak reflections, if you do much longer exposures, then it adds more of these subframes to reduce the noise. So your readout noise on short exposures doesn't vary that much from the long exposures. And that's really important, because in old CCDs, the longer you expose, the higher the dark current, the more it swamped out your signal. So if you do a 1 or 2 minute, 3 minute exposure, your read noise is not that much different from if you're doing 10 to 20 second exposures, because of the way we're doing the integration of the signal. And so what we also do is we do a polynomial fit to the non-destructive and destructive read. So we get a better, more precise measurement of what that pixel value really is. So that's the big advantage of the CPAC, is you can do this type of measurement, both integration and photon counting. That's the point. The goniometer you'll see we go in there is a kappa goniostat. It's got a unique geometry where you can move 4 different angles, we call them. That's why it's called a 4-circle goniometer, and I'll show that when we go inside and work with the hardware. But it makes it, for me, easier to retrieve crystals. I'll show you a short movie of that. You can move the detector offset to any resolution. So with a lot of the system, the detector is fixed. They're huge at the beam line, right? So it has a huge solid angle, so you get whatever resolution you want for the most part. But in-house, it used to be hard to get certain resolutions based on the detector, because not many of them had a 2 theta offset. You can get out to atomic resolution on this system, so you can do small molecule work on this system. You can get out to 0.8 angstroms, and 0.8 or lower, actually, with gallium. So it's about half the wavelength, yeah. So it's really nice. You can get to any data that you really want. And I've got some examples of how you can use a kappa to improve your data optimization. So this is how I handle samples. So with the kappa, you can go straight up and down. You look on your system, the nozzle is collinear with the goniometer head. So the beam stop we'll see and the collimator are magnetically self-locating, so they pop on and off very easily. And so it's easy to pull them off to handle your samples, and it opens up a lot of room. And what I do is just use tongs. And it's easy to put the crystal on, and then you're ready to go. So you're collinear with the cold stream, so you don't have to worry about the height for the most part. And you just pop it on. To retrieve it, it's just the opposite. So I use tongs coming back to actually retrieve the sample. And all I do is go up, open it up to seat it, take it off, and put it on. And my success rate with this is almost 100%. It's actually really easy to mount and unmount the crystals this way. So the kappa doesn't go fully inverted, so some of you in the past may have worked with a system that had an inverted phi. And so that's really easy to use vials with to mount crystals on and off. You can use vials on the kappa as well. You can go above horizontal, and you can get to about 100 degrees overall. So you can do it, but I think tongs are actually easier to use. So if you haven't used those in the past, they're pretty easy to get used to. So that's the hardware, for the most part, you'll be using. And then when we go inside the X-ray lab for the hardware sessions, we'll talk about how you would use the system, open up, put a crystal on, things like that. The software flow that you guys will work with is just, there's communication software, hardware control software, and data collection software and data reduction. You guys will be mostly concerned with PROTEUM 3, which is our data collection and data reduction software suite. These other programs are mostly what Joel is going to use to keep the system going. Measurement Server is a server app that controls the instrument, so it communicates between the server computer and the instrument itself. BIS is sort of a conduit between the measurement server and PROTEUM. So these programs just have to be running in the background. You don't have to interact with them. And there's icons on the desktop, at least I think there are, we'll look for sure, where if they're not running, the program will come back with an error and you just have to start it. And I'm pretty sure they'll be running. You can just leave them running in the background. So for the most part, you won't deal with any of these other programs. Diffract is actually a configuration suite and alignment suite for the system. So PROTEUM 3 is basically all you're going to use for data collection. The software itself is a lot like the other software packages that are developed these days. Phoenix, CCP4. It's Python-based, and it's in this sort of app or plug-in mode that a lot of programs have gone to, so that you have a series of independent programs that are in a GUI wrapper. And so it'll look unfamiliar, but the layout will look familiar because it's very similar to other programs in that sense. It has a PostgreSQL database. So there's a database that keeps the information while you're going through your experiment. It's not necessary to keep the database entries around. So as you do things, information is written to the hard drive. So if database were to be corrupted for some reason, or I would delete an entry, you're not losing information. Everything is stored to the hard drive. But the database is there just as a bookkeeping tool for you to go through your entries. The system has a server-client platform. So if I'm somewhere in the building and I'm on the same network, local LAN as you are with the server, I could actually log in and see what's going on. So it's that server client. I don't know how you guys are set up as far as a LAN system or VPN, or if that's even on the network. But it is possible to access the system remotely. I use remote desktop a lot. It's a Windows system, so if I'm at home on the weekends, I can log in through our VPN and actually control our system. So it's pretty nice, actually. And then there's a Shellix software suite that we have. We have an exclusive deal with George Sheldrick for structure solution. If you guys are interested, I've got some examples of SAD phasing you can do on a system and how that's incorporated into our software, and I will be doing that tomorrow. There's a configuration file for your system, so you can configure almost any default in the software. So you can set it up to how you want to do things. You can configure chem and bio separately. So if you're going to get into some chem stuff, we can configure those differently. So Run Apex will run one configuration, PROTEUM will run another configuration. And you can do things like set up automated runs for indexing. So we have an auto mode in indexing I'll talk about in a second. So you can set up runs that you would always do. So I typically do 2 shells of 3 degrees of data. So I'll do phi 0, 3 degrees, and then rotate phi 90 degrees and do 3 degrees and index off that. So that gives me a decent starting orientation matrix in most cases. But you could index off one frame if you wanted to. It will do that, but it's just not going to give you a great orientation matrix. And it's always better to rotate to a different area of reciprocal space anyway, just to see what the diffraction properties are, because a lot of protein crystals have an anisotropic nature to them. And so one direction will look great, and you rotate 9 degrees and the diffraction will be terrible. So it's good to know that ahead of time. So you can set up runs for yourself. So in other words, I've got 2 theta offset of 10 degrees. I've got my starting crystal detector distance at 70. I'm telling you to do 3 degrees. I'm doing 2 sweeps, which is 0 and 90. and then I set in a time. So then every time I index, I do the same scans. And I can change some of these parameters, and I'll show you that, to suit whatever crystal I have on, but I run the same 2 scans all the time. So you can do that if you want, or you can just collect your own scans. It's up to you. The sample database has a default account, which is guest. So you can always log in as guest, but I think probably with as many users as they'll have at this facility, then you'll probably set up individual accounts for yourselves. And so we have a simple, what we call the user manager, which sets up user base for the database. And so you can design specific groups and users within those groups. So the problem is if you have so many users that the database just keeps getting huge. And so when you go to look for your own sample, you've got to go through all these other samples. Where if you set up the multi-user support or multi-users, then you only see your samples. So when I log in, I only see the samples I've created. So that would be something that you will probably do at some point. But if you forget, and I don't know how to log in, guest will always work. And so what there is a frames directory, which holds all the raw data. And then within the frames directory are subfolders, which are usernames. So if under guest, it would be C frames guest. Okay? So to do anything, I have to open a new entry in the database or open an existing entry. And so you'll see at the software at the top, there's 2 little icons that allow you to open or create an entry in the database. The little sort of just sheet there that's a new entry. The open folder here is opening existing entry. So when you go to get in the program, that's what you need to do first step after you log in. And so if you open the sample menu, you can do the same thing. There's just new and open. And that's just new for a new entry, open for an existing entry. So when you create a new entry, what it does is pops up this little window. And it has the path already. So it'll be C frames, and then it'll have the user account. So in this case, it's demo. That's the user I'm using. So as soon as I start typing in here, you'll see the same come up down there, and it'll create a folder in the demo folder, subfolder, whatever I type up here. If it's not there, it'll create the folder. If it's there, it'll just point the path there. So as I type in the name, then it creates a folder for me, and that's a new entry in the database then. An existing entry, if I open the open folder, it just shows all the entries, and then I just highlight the one I want. This is sort of like a spreadsheet, so you can sort this based on when it was last modified, name, etc. And so you just click the one you want, say, oh, OK, and it just opens that entry. Once you do that, then it opens up all the applications that are available. So you log in, you create an entry or open an existing entry, and then you have access to all the different icons. So it's a little hard to see on here, but you'll see when we're in the X-ray lab. So we have a toolbar that's on the left side that has menus that take you through the experiment. So there's setup, screen, collect, reduce data, examine data, solve structure, and report. So you just select the app that you want to run. It runs within the GUI, just like most of other crystallography software. Indexing is just what you do with any crystallography software if you're doing data collection. So you collect some frames, you harvest some spots to get some reflections for indexing, and then you try to find the orientation matrix. And so the program offers 3 different types of indexing, and I'll go through those: difference vector, fast Fourier, and a program called CellNow. So you have different modes of indexing you use to make it easier to index your sample.
So how efficient it is to pick up the weak spots?
So it's really efficient to pick up the weak spots, and there's some filtering tools that you can do to aid in trying to get an appropriate reflection array. So the hardest thing indexing is trying to get rid of the noise and keep the real Bragg reflections. And so the program has some filtering tools for that, but there's another program called RLAT, which is really nice. I'll talk a little bit more tomorrow. So we'll go through that. And this is RLAT. So RLAT is a program that graphically displays the reflections in reciprocal space. And this is actually a twin structure where it's hard to see, but the red is one domain and the yellow is a different domain. And you can actually modify the reflections manually by doing this. And I'll show some examples of that. And this is really, it's pretty straightforward as far as it's not a high-end graphical display, but it's really great at modifying the reflection rate and getting rid of noise that you'll pick up on very weak scatterers. We have this should be PROTEUM 3. We have a SAINT program that is our integration program. And this is very similar to XDS in that it does a three-dimensional profile fitting rather than a two-dimensional profile fitting like Denso and MOSFilm do. And so because these days with the CMOS sensors, we do a lot of fine slicing, so I rarely go over 0.5 degree rotations when I do data collection. I vary between 0.2 to 0.5. And so with a fine slice, because it will give you usually better data if you do a more fine slice and help you separate the Bragg reflections, particularly with the long, you have a long unit cell axis. And so the three-dimensional approach is a much better way when you're doing fine slicing of integrating your data. I'll talk a little bit more about that. And our data actually handles twin data automatically as well. And we can talk about that a little bit more so tomorrow. We have a scaling program called SATABS, which was written by George Sheldrick. And basically, it's like every other scaling program. So the idea of scaling for your protein data is that you're trying to put all the reflections on a common scale, make them internally consistent. And so there are things during the data collection that will add systematic errors or even random errors to your data collections. Absorption effects of the crystal. If the crystal's bigger than the beam we were talking about before, you'll have variations in the crystal volume as you collect data. That will cause systematic effects to your data. Incident beam in Himeji is not going to be a problem for you. That's more a beamline thing. Your beam's pretty stable. So there isn't much variation in the intensity coming through. And crystal decay, you will see decay on this system. It's not going to be like the beam line. It's not going to go in a couple minutes. But you will see significant decay over time. And so you should take that into account. So that's when I was talking about exposure times. If I'm going to collect 2 minutes, and I'm thinking, well, if I do 3 or 4 minutes, I'll get better data. You might not, because your crystal may die by the time the data collection is done. So you might have to keep that in mind a little bit, that I'm not talking minutes, but if 12 hours, 13 hours, the crystal's going to show significant radiation damage. And so you have to keep that in mind. So you can collect longer, but every sample's different. Every target has a different sensitivity to incident radiation. So just keep that in mind when you're doing the data sets. When I first started using the METALJET, I got caught in that a couple times trying to push the resolution, and I ended up killing my crystal. So just keep that in mind a little bit. The scaling can also hand twin data, so it will handle twin data and separate twins. And the error model it uses is very similar to ScalePack. So it uses a chi-squared model to try to model so the standard deviations represent the spread in the reflections, and I'll talk a little bit about that in a second. We have a space group and statistics program called XPrep that's written by George. It's a data analysis tool, and we'll write out different formats. We have a GUI that does basic stuff and then takes you through trying to find a space group, for instance, very similar to Pointless, Aimless, or XTriage, if you use those. XPrep was actually the first one that started doing this kind of stuff, looking for rotational and translational specifics for trying to find space groups. And you can also unwarp and convert images. So you can use this to do beamline data. So if you really like PROTEUM and you think it gives you good results, you can bring your beamline data and reduce it with PROTEUM. So we convert all the standard beamline detectors. And mostly they're all Dectris now. There aren't too many different kinds left anymore. But we support CBF format. We're not supporting the, the metafile format, H5 yet, but that the Eiger has, but we'll get to that some point soon. You can also use XDS to process your data here. So we write out CBF format. And we work with Kai Dieterich. So he wrote into the XDS or generate XDS script the support for Photon 2. So if you wanted to use XDS, for instance, you could with our data. And what's nice about the converter, I'll talk about more tomorrow, is that you can update the frame header. So beamline data sets are notorious for having the wrong beam center. And so you can update any information you know about in the header when you make the conversion. This is the Bruker Instrument Service. I won't talk too much about this, but this is just one of those background programs that you have that actually give you information about what's going on. And again, this is more information for Joel than it is for you guys. But it's a program, it's a control program in background that monitors everything, and there's a log file that comes out. It's nice, especially when you're troubleshooting, to figure out what's going on. So as I mentioned, other programs will reduce our data. And so you can use, for instance, HKL if you wanted to. You have to pay for it. But you could use HKL 2000 to process the Photon 2 data. XDS you can easily use. You have to have a Linux or Mac to run it. It won't run on Windows. But you could convert the frames to CBF format and then simply run those into XDS if you wanted to use that. MOSFilm I've never gotten to work. They've never supported our frame format. And so with the Dials project that started up in the UK, which is a new integration data reduction suite that's part of Diamond Beamline there, that they have a consortium over there, MOSFilm's kind of going away. There's not much support for it anymore. Harry Powell left the MRC, and he was the one that was doing most of the support. So I think MOSFilm's pretty much going to die out. And it does a two-dimensional approach to integration. So with a dexterous push at the beam lines where you're doing this ultra-fine slicing, two-dimensional just won't work very well. And so MOSFilm just can't handle those frames as well as XDS or Sync can. OK, so that's just an overview of the data hardware and just sort of the layout of the software. What I want to do now is get into some of the specific applications and kind of how you're going to use the system. So crystal indexing would be the first one. And so inside the program, you would go to the screen menu, and there's a plugin called Determine Unit Cell. So when you index, what you're essentially trying to do is figure out how the domains of your crystal are oriented relative to your hardware. So then you can predict where the spots will end up on the detector, and that tells you where you should integrate for your data. So once you get that orientation relationship, then you can figure out where the diffracted Bragg reflections will be. And so that's what indexing is doing, and it gives you what's called the orientation matrix. And so just telling you how your crystal's oriented. And so what we have in here is two different modes. We have the auto mode and the manual mode. The auto mode does everything the manual mode automatically. So when I was talking about setting up those predetermined runs, what you could do is in here, if you had those runs set up at a certain exposure time, you could just hit go, and it would collect the data, harvest the spots, or try to index, do refinement, do a higher symmetry search, and to do a final refinement. So it will go through all the steps that you would have that you would do manually. So what I would suggest that when you're working with a known target that you've indexed, diffracts well, you know what to do. What I always do is use the auto mode. And I just click go. I come back in 5 minutes and see how it's done. If you're doing an unknown, I'd probably do it manually just because I just don't know how good the diffraction is and if there's any problems with the diffraction. So you have the option of using either mode, and there's a manual step that's in the automatic mode that you have access to every step. So the methods are difference vector, fast Fourier, and least squares. And difference vector is sort of the classical approach. This is what XDS does. And so it looks at spacings between reciprocal lattice points and says, well, there's a histogram and says there's a lot of spacings that are at this distance. That could be a unit cell vector. And so it does that, tries to find potential unit cell vectors, and then tries to build a cell from that. And that's a classical method of indexing that's been used for decades. And so that works really well if I have a limited number of spots, but I have a wide angular range. And that's why it's used mostly in small molecule work. But it also can be very useful in protein, especially when you have weak diffractors, because you'll have a limited number of spots, and you may collect more data to try to index off that. And sometimes the difference vector actually works best. The other method is fast Fourier, and that's what you're probably more familiar with, because that was originally developed by Michael Rossmann for a program called DPS, and that's what Vladik put into Denso and now HKL. And so what that does is actually looks throughout reciprocal space, takes a vector and does a Fourier transform in different directions to look for a periodic nature of the spacings between reciprocal lattice points. And what you end up, if you're down a unit cell vector, you get almost a delta function. And I can show that in our lab. It's kind of cool. And you can see how the fast Fourier works. So it looks throughout reciprocal space looking for potential unit cell vectors and then tries to build the cell from that. Least squares is a unique program that George wrote to help work with very complicated reflection arrays. So least squares is actually an auto detwinning program. What it does is it does a brute force method, kind of a combination of both, to find a unit cell based on a subset of a reflection array. So a lot of times if you've got satellite crystals or crack crystal, you'll get almost a second domain, diffraction domain. And so that can really screw up your indexing. So what least squares does is try to find a cell from the subset of a reflection array. And then if you want detwin, it actually rotates that cell to try to find another cell that matches the rest of the reflection. So it will automatically detwin crystals for you. But it's really helpful when you have problematic reflection arrays or diffraction, because it's really good at selecting the subset you should use to index. And so it will do that automatically. And so it takes longer, but it actually gives you a little more flexibility, a little more to expand how you can index off a particular reflection array. So the first part of the indexing is collect data. So I said you can set up automatic runs, but not every crystal is the same, right? They have different unit cells, they have different diffraction properties. So on the fly, you can actually change the distance, crystal detector distance, and the exposure time to match the sample. So I run the same 2 runs, or how many runs I want every time, but on the fly I can change the parameters that affect the indexing. So if I come in here and I've got, usually I have this at say 70 millimeters, but I've got a really long unit cell. To collect my indexing runs, I can move the distance back to say 110 millimeters and collect the same 2 runs. So I could just come in here, I could change these parameters, hit run or finish, and that would do the auto mode just from that point. The other parameters pretty much just stay the same. For the CMOS, it'll have the defaults. You don't have to worry about those. Like I said, I usually do 2 runs of 3 degrees separated by 90 degrees in reciprocal space. You can index or set up your index runs however you want, however you guys typically do it. You can add more or less data. Our file names are all the same, and that's so the program can recognize what we call runs or just angular ranges for your crystal data collection, and the number of frames. So it's frame name, run number, frame number, and the extension's always SFRM. So the program knows how many independent runs you have and how many frames are in each run. So to harvest spots is the first step. So I've got my data, I want to collect some images. So at the very top, you just put in the first image that you're going to use. It can be any run. It can be actually anywhere within the run. So for instance, if I have 300 frames, I collect a bunch of image spots at frame 1 to say frame 10. I can move to frame 300 and do the same thing. The frames don't have to be sequential like they do in HKL. You can collect from anywhere in reciprocal space. The next one is the number of runs in the frame. So if I put in 2 runs here, it's going to see if there's 2 runs, and it's going to collect that number of frames. So for my indexing, I usually do 2 runs of 6 frames each, 3 degrees, half-degree rotations. I put in 2 and 6, and it'll harvest from both runs. The next one is just go to image. That means that's the image it's displaying. So when I index, it'll display that image. And then you have I over sigma I, so that's my cutoff for how strong the reflections have to be over noise for me to harvest. And you can play around with that to get the number of reflections you want. There's also a little what we call smoothing. And so what smoothing does is actually reduces the resolution of the image to sort of blur things together. So for instance, I've got a crystal that's cracked and I've got a split profile. So that can be really hard to index off of because you've got two peaks next to each other and the program might actually harvest both of those peaks. So what smoothing does is blurs the image so those become one, and it allows you just to harvest off one of those sort of in between those two peaks. But what it also does is lower the signal and noise of all the reflections. So I can play around with these two parameters to get the subset of reflections I want for harvesting. So we'll notice when we're in there, if we click smooth images, it harvests a lot less reflections. So I can play around with these two to sort of work on getting the right, so to your question, try to help get away from just getting all noise. This is exclusion shell. So if I've got an ice diffraction and my crystal hasn't frozen quite well enough, and I see either just powder rings or I see actual ice diffraction, I can exclude those from harvesting. And I can do it by doing the shells. So I just put in the shell that I don't want, and it won't harvest from that area. I do this a lot with beamline data because with the big detector, a lot of times you get diffraction all the way out, and you just don't need that much when you're trying to harvest for indexing. So we'll cut off the resolution at 3 angstroms because that's more than enough to index off of. So it gives you a way to exclude shells within the actual image itself. At the very bottom, it has a color code for the reflections. So you can harvest like 10 different reflection arrays, and it'll just add a different color to it. And what that means is if I were doing a twin, for instance, I could make one reflection array, one color, and then color code another reflection array and index off both and have the orientations of both domains. I would pass that on to the integration. It would automatically detwin the data for me. And then one other filter down here is spots must span reflections. So a lot of noise peaks, if you harvest, will be single image, single pixel in some cases. Zingers used to be like that, right? So by telling the program that spots must go between images, and if I do a small amount of rotation, that's pretty much going to happen on all my spots. They're not going to be on a single image. That will help get rid of noise. So that's another filter that you can use to sort of get rid of some of the noisy reflections. On Pilatus detectors, at the gaps, right on the surface of the gap is notorious if you're trying to harvest there. Because if you drop the I over sigma too low, what you end up getting, because the program looks at that conversion between no counts and counts and thinks it's a spot. And so you'll get all these false reflections harvested right where the gaps are. And so this will really help with that, to make sure that they have to span images in the same place. So navigating through this, what you see down here is a series of buttons. So arrows move to the next step. So when I'm in any of these windows, there's the next step, previous step. So in other words, if I'm harvesting and I hit the arrow, it'll harvest the reflections and go to the indexing window. So that's the next logical step. What this step here, if I go back from harvest, it would go back to data collection. So it would go, the arrows go to the next logical step. Finish takes you automatically from where you are. So if I go into harvest and I change something, I can just then hit finish and say go, and it'll do the auto mode. Harvest, or this button here, would be index, and indexing takes me back to the main menu. So I'd harvest spots and then go back to the main menu, and I could do things. I could go in RLAT, for instance. And then cancel just takes you out. So that's how you navigate through the windows when you're doing it manually. So you either do next step, this is what I typically do, or you can do the auto mode from any step, or you can just harvest and get back out. So then you're up to indexing. So indexing is laid out in a similar way. At the top, it's a little hard to see, but you have a color-coded and then a number of reflections. In this case, it's I think it's 800 and something reflections. So it tells you what what a reflection array you have, what color and how many reflections you have. Then go to image is the same. It just displays which frame is being displayed in the window. You have I over sigma I, same thing. As you have in harvesting, you can adjust the signal noise to cut off more or less reflections. You have a resolution cutoff, so if you want to limit the resolution here, you can for indexing. You have some classical filters. We already talked about spots must span image. The other ones are a spot can't go over too many pixels. That's sort of try to get rid of ice rings. So if an ice ring that's really strong, the program might actually pick individual parts of that ice ring as a reflection. And you can tell it not to do that. I don't use it all that much. You have to be careful. If you've got a really long unit cell axis and the spots are running together, it will throw those out as well. So you have to be a little careful with that. And this is spots must be whole as a throwback to the old days where at the beginning or end of a scan, if you have partial spots, it'll throw those out. Your offsets in the frame header are not going to change. It's not like a beam line. So the beam's not going to move all around. So most of the time, the offsets you'll never have to worry about. But if you were doing beamline data or something just didn't look right, you can manually change the offsets. So these will pop up. These are in offsets of pixels or millimeters. Yeah, for the XY position of the beam, it's millimeters. So if you know something's wrong, you can change it. But on a home lab system, that's not going to vary. And then the pitch, roll, and yaw are the detector offsets. So how planar or how square the detector is to the incident beam. And that's not going to change either. So you won't have to worry about those. But you can. If you know you have to change this, you just click manual and you can change it. And so then you have the three methods down here. We do difference vector and fast Fourier by default because they're pretty quick. I do those typically anyway. And then you can also do least squares, and we were talking about that before. So the one nice thing about least squares running from here, from the GUI, is that you can specify a specific cell. So if you know a crystal has a specific cell, but you're having trouble indexing, whether it's cracked or has a satellite, you can go into click least squares, and you can specify what the cell should be. And the program will try to go out and find a subset of reflections that match that cell. So I've seen, and people have asked about this, and this is probably for us the best way to do it is because then you're not trying to get that cell from the whole reflection array. Usually if you can't index, it's because there's some inherent problem with the way reflections were harvested. So that actually is nice. It takes a little longer, but if you're pretty specific about your cell lengths, it runs pretty fast. Once you've indexed, then it shows you all the indexes based on the method you selected. So at the top is difference vector, there is fast Fourier, and what it gives you is a HKL histogram. That's how many of the observed reflections match within tolerances the predicted spots. So the higher, the better, right? So the more your observed data matches your predicted spots, the more accurate the higher accuracy or missing the word I'm looking for here, but confidence you have in that the index is correct. And so 90% is great. Typically what you will see is 60% up is pretty good. A lot of times what you'll see is you'll have a long axis that some of the spots may be overlapping, and so you might have that less in that direction. So you might see 50, 70, 70, and that's okay. You can pull that in by refining. If you see one of the percentages for the comparison between the HKLs around 20%, the odds are you're not going to be able to pull that in, and it's a wrong unit cell. So if you're above 50%, you got a chance to pull that in. But if you're way down in one direction, then something's wrong. And typically what will happen is, if you look in RLAD, it'll tell you right away. What happens is that you have two short axes and one long axis. And the two short axes are really to resolve the spots, but the long axis, all the spots are running together. And so the program's having a hard time picking up where the centroids are for the spots. And so it just can't determine what the length of that last axis is, and that's pretty common. That usually means you're either too close with the detector or the mosaic spread is really high in that direction and you have to make adjustments to that. Then what you do is you do a least squares refinement of the reduced triclinic cell, and that is to let all the cell parameters vary. So all the unit cell constants can refine to give you the best value for those constants. And then you use that to try to find a higher symmetry. Since most people don't collect a lot of data when they index, we restrict you to only refining certain things. So the most important things are beam center, detector offset, the crystal detector offset, and the domain orientation. So those are what we let refine. So least squares works really well when you have a high data to parameter ratio. But if you don't have a lot of data and you're trying to refine 10 different things, it just doesn't work that well. So if you only have a couple hundred reflections, we restrict what you can refine to only the most important parameters for refinement. Then once you have the reduced cell refined, then you can do I'll talk about refinement a little bit. So when you refine, all we would do is click the refine button down here. We have a tolerance. How many of the reflections that you harvested are going to be used? And there's a little slider bar here that says more reflections, less reflections. And so what I do when I come in is I use the reflections the program suggests, and I hit refine. And that does the least squares refinement, and then I'll add more reflections as it improves. So you can just slide that bar, and actually you'll see more reflections come in anyway because the tolerances will get better, the orientation matrix gets better. And so the differences between the observed and calculated are less. So what you can do then is after you refine a couple times and move this up and add more reflections and see if that improves the refinement. You have RMS values for the differences between the predicted and calculated positions. And these are like chi-squareds if you're used to HCal, where it tells you what the distance is between the observed and calculated in plane, which is xy, so in the plane of the detector, and through plane, which is the rotation, the angle. So values for these should be as low as possible. So when I'm refining, I look at these values and see if they converge. So I'll hit the refinement button a couple times, change the number of reflections that I'm using, and see if these converge, and they should. So you want the RMS XY to be less than 0.3 millimeters, and you want the angle to be less than a degree. If they get too high, then you're just too far away to actually pull that in. And so you'll see the values displayed every time you hit refine. And so that gives you a way to show that the cell's improving because the agreement between the observed and predicted positions are improving. There's a button here called histograms, and you can actually look at the air distributions of all the spots. And this is actually really interesting because it'll show you how well in HKNL, the indices, how close you are between the observed and predicted spot. And then in plane, XY, and then through plane. And it'll give you where, if you're having troubles, where it is. And one thing that's kind of cool is if your goniometers were off, for instance, you would actually see a shift in the rotation angle in the airs away from zero. So there's a lot of information in the air histograms. And you can actually look at the individual spots. So if I click on any of the bars, it'll actually show me all the spots that are under that bar. And I could select these, delete them, and then go back and refine. So if you only have 100 reflections you're trying to index, a couple of reflections can throw the refinement off. So if I see a couple outliers, I'll just highlight those, delete them, and go back and refine. And a lot of times the refinement will improve. So this is a good way to manually, again, modify the reflection array. And then transforms, which is the box right here, will transform the unit cell into any convention that you want. So for instance, say I had a orthorhombic cell that was P21 to 1,2, and I know I have to switch two axes to get the right convention. I can do that here, and the program will do it for me. I can switch A and B, I can switch B and C, I can double or half a cell length. So I can do all that here, apply the transformation, and then go from there. If I try to put in my own transformation matrix and I'm changing the hand, it will come back and warn me and say you're not right. It'll do that automatically for you. So if you have to make a transformation, you can do it after the fact too, but if you know you have to do it before, you can do it here. Because what happens is most indexing, it'll do smallest to longest cell in A, B, and C. So it might be that the longest cell actually has to be in the B position, and you have to make a transformation. So once I've refined my reduced triclinic cell, then I want to look for higher symmetry, and every crystallography program does this, right? So what it does is says, I have my reduced triclinic cell, what are the possible cells that I can transform to? And so then what it does is it looks at the cells that I've transformed and how do they match the Laue constraints for that point group symmetry. So if I transform triclinic to tetragonal, for instance, I know that alpha, beta, gamma have to equal 90 and A has to equal B, not equal to C. And that's the Laue constraints for tetragonal point group. So the program looks at that and says, okay, how close does the cell constants match those constraints? And if there's a close match, I'm going to say it's good. You can use this. That makes sense. If it's in green, that means the program thinks it's acceptable. If it's in red, that means that the program thinks, yeah, you can transform it there, but it's really not that cell. And so, like every other program, we assign a figure of merit to that. And so from 0 to 1, the higher the better. And so anything over 0.3 will look to be green. Anything below that will look to be red. So if you see something with a figure of merit of 0.01, 0.02, there's no way that cell is correct. But if you see that around 0.25 or 0.29, it might look red, but because of the diffraction, it might really be that. So if the diffraction is really poor, the program's just having a hard time, the angles just aren't refining as well. So that's something you can pull in. So it's something to think about anyway. But if you're down to 0.01 or 0.02, there's no way that cell is going to work. And you can select any of these cells and then transform it and then go on. So for instance, there's cases where it looks like it's tetragonal, but it's really orthorhombic. And so you can just highlight whatever cell you know it to be and then go on from there. It'll transform that, and then you go to the final step, which is refinement. And then in the final step, I apply the Laue constraints. So for tetragonal, I make sure that A is equal to B and alpha, beta, gamma is equal to 90. So then at the final refinement, that's when I apply my Laue constraints for that point group symmetry. Questions on that? I know that's a lot of information. But, and we'll go through that, some of this when we go put a crystal on this afternoon. And this is stuff that you will forget for some of these buttons are. And so when you have questions, just let me know. And like I said, we can do remote training where you're not sure about something. I'll go through it with you. The way you learn software is to work on it yourself. And so when you start playing with the software, you'll get more familiar with where everything is. I'm going to make I make little PDFs of all this stuff, and we have a manual. It's pretty good, but it's pretty big. So I'll make PDFs of all the individual components of this, so you can reference these to look at them. Do you guys want to take a quick break as I go through, or keep going? It's up to you guys. What time is it? So I can keep going. But it's up to you whether we can. Okay, we'll keep going. The next thing. So there's two things I'm going to talk about this morning. So it's a data collection strategy and how you would use it, and data reduction, SAT-abs, and where you go from there. Tomorrow, what I'll talk about is what you do with the data when you're done. How do you get it in other programs? If you're doing synchrotron data, how do you convert the frames? And things like that. Okay. All right. So the strategy program, we have an automated strategy program. And with a kappa, you'll figure out right away why we do that. Because at first you won't have no idea what the kappa angles mean if you haven't worked with one. I know now where to go and everything, but when I first started working with a kappa, I mean, you'll see everything moving around. It's 4 different circles that you can move around. And so it's not obvious right away. And so we have an automated program that will help you calculate the strategy for you. So what we do is we tell the program to find, it's sort of a genetic algorithm, and it finds how to collect the data based on the unit cell. And then it asks the program, or BIS, the instrument server, what's allowed and what isn't. And it kind of goes back and forth and refines those runs to optimize data collection. It knows where to go because it knows opcode. It has a collision map. It knows exactly what hardware is there. So it's not going to suggest a run that isn't allowed. And it finds the strategy based on what resolution you want and what your cell, your orientation matrix is. You can do specialized things I'll talk about here, but mostly you'll probably just use it to collect a standard data set. So why do you need a collection strategy? Because it's easy to figure out how to make the best use of the instrument time. So at high symmetry, tetragonal lysosome, I can do 90 degrees in almost any orientation and get pretty much a complete data set. But in monoclinic, triclinic, even orthorhombic, it's not trivial, depending on the orientation of the crystal or how the crystal's mounted, to get a complete data set. And so it's nice to have the strategy program to do that for me. What you need is the unit cell that you have, and you get that from indexing, orientation matrix, your resolution limit, what you want to get out of the crystal, and then what the experimental parameters you're going to do, rotation angle, exposure time, what distance you're going to be at. And then what kind of experiment you're doing. Am I just doing a native data set? Am I just screening? Or am I doing something more specific like a SAD phasing experiment? So this is what it looks like, and this is not really a great representation, but gives you an idea. In the lab, you'll see it more. This is the goniometer. There's where the goniometer head sits. There's your kappa arm, and this swings up like this way, and then omega swings this way, and we'll show all this in the lab. Your source, your optics, and then your detector, of course. So the advantages of a kappa is, first and foremost, is that you can orient the crystal in almost any way you want. And so that allows you to do something that's called random or true multiplicity. So as I collect a data set, you're actually better off collecting in different orientations, because then you can model what the shape of the crystal is, rather than just having the crystal spun in the same orientation multiple times. And so that helps with both your absorption correction and scaling, but also if you were to do any kind of phasing experiments, it really helps to get a true representation of the reflections and the shape of the crystal. So that's one of the main reasons. Also, you can get specific, you can do specific things, like I'm having trouble with overlaps. I have a really long unit cell axis. I can align the rotation axis along the long axis, and then I can minimize my overlaps. And with a kappa, you can do that. With a single spindle, it's really difficult because it depends on how the crystal is mounted. Right? I used to work in myosin S1 years ago at the beam lines, and they used to grow on these thin plates. And the long axis would grow right through the plate, the short part. So you could never mount it at an angle or anything. It always laid in. And we had trouble in beam lines because as you rotate that, the long axis, you get tons of overlaps. And so what we ended up having to do is make 90-degree loops so that we could orient the crystal differently when we were doing the single spindle. With a kappa, you don't have to do that because you can almost put the crystal in any orientation. And then I like it too because it's easier to flash cool. So that, as I was showing earlier, I can go at different positions of the crystal to get however I do, either tongs or vials. Makes it easier to get at the method I'm using for cooling my crystals. It also helps with what's called the blind region during data collection. And as it turns out, if you just do a single rotation, you end up missing the data, a certain amount of data that you just can't get, depending on the resolution, the wavelength you're at, and then the symmetry involved. So this is a plot that shows, this is copper radiation 1.54. This is around selenium, that's about 1 angstrom, and then down to moly, about 0.7. So 1.34 would be in between the copper and around the selenium edge. And so what this shows is that if I'm out at 2 angstroms, just by a single rotation, I'm going to be missing 3 or 4% of the data that I just can't get unless I reorient the crystal. And so that's what kappa can help you do. It can give you a different orientation that will allow you to pick up the rest of the data. And here it's just showing the blind regions. If I do a single rotation, there's just regions along a certain axis that I'm going to be missing, depending on the symmetry. The higher the symmetry, the less the problem is. But if you get down to monoclinic, triclinic or even orthorhombic, you'll end up missing probably 4 to 5% depending on the resolution you're looking for. You can also do things like orient it to avoid overlaps or long axis. I just talked about that. But you can also optimize your data collection. So for instance, if you have a high symmetry hexagonal P6 upon MMM, if you orient the rotation along the c-axis, you only need 30 degrees of data to get a complete data set. But if the rotation axis is in the AB plane, you need 90 degrees. So that's a huge impact on the amount of data you need, right? If you're just trying to get a basic data set, I can get it much faster if I orient the crystal in a specific way when I do a data set. So it just helps speed things up. The other thing that's important in data collection is resolving your spots. And I see this a lot from beamline data where people don't, because a lot of this is automated now, they don't pay enough attention to this. You can, if you're too close with the detector, you can get the spots where they're overlapping quite a bit. And you have to be careful of that. And so you want to look at, and we've got a tool, and I'll show the graphical tools of how you look at reflections on the images when we're in the X-ray lab. But what you want to do is make sure that you're getting proper separation of your reflections. And this is, in a home lab system, it's a little different because we use a focusing optic instead of a parallel beam. So at beam lines, you got these tiny beams and they're parallel, so the beam doesn't diverge as you go away from the sample. And so the spots really don't change. What you see is what you get off the crystal. The home labs, increase the intensity, we use a focusing optic. So and I've got a slide up here showing it where the rays are focused to the sample where that's the maximum intensity, but as you get away from the sample, they diverge. And so the spots get bigger the farther you're back with the detector. And so you have to take this into consideration, that the divergence you're using and what the unit cell size is. And I'll show you a table of that. One thing you can do to get better separation is you can pull the detector back farther. You can do a smaller rotation range. So instead of 0.5, you can go down to 0.2. That'll help bring less reflections coming through on a given frame. And you can decrease the beam divergence. And so we have a set of collimators you use. So we have pre-aligned collimators at different divergences. And I'll show you a table of that. And then, so all you need to do if I want to go to a lower divergence is just pop a different collimator in. So this is the idea of the optics. So you have your rays coming in, they strike the metal mirror, and they're focused. And the focus point is the position of the sample. And that's maximum intensity. And so the divergence, or you'll hear crossfire is the term at the beam lines, is just the width sort of the focus rays coming in. And so after you get past the focus, it starts diverging. And so that means that your spots, so at some point I could hold the detector across the room and I couldn't resolve the spots because they're just keep getting bigger and bigger. So if you look on here, this is why we use focusing optics. The higher the divergence, the higher the intensity. And that's how we've maxed out that's why we're at where we're at now with the home lab systems. We've used a highly divergent optic. But that only goes so far. So here's and it's really hard to stand this, there's a lot of focus, but it's beam divergence and just the cell. And so as you get to higher and higher cells, you've got to drop the divergence, the longer cell edge, because otherwise you just won't resolve the spots. So this is I'll show the 3D viewer. This is how a lot of times I'll look to see if the spots are really resolved. And I'll show that in the X-ray lab. This is kind of a table that I use as a guide to what the collimators are, sort of, the rough divergence for each collimator and what that means to my data collection. So you have 4 collimators, I think, in your system. So wide open is 7.6 millirads, so that's maximum intensity. You have one that's 0.3 by 17, which is around 7 millirad. You have one that's 0.3 by 10, which is about 5 millirad, and you have one that's about 0.2 by 6. The 0.2 and 0.3, that's the scatter shield, or the exit collimator, and that kind of shapes the beam a little bit. The full width half max is really small, so it's about 70 microns. So almost all the counts are in that because it's a Gaussian profile. But there are some tails on it, right? And so those are kind of clip the tails off of the beam that's coming out. So this is what happens to the intensity. So I go full, say on a relative scale of 1. If I go down to 5 millirads, I've lost about half the intensity. But I'm able to resolve a much longer unit cell. And so that's what you'll have to go by, is you'll learn this over time, is that, all right, my unit cell's around 250, what's the best divergence to collect this at? And sometimes you'll be at sort of in a gray area, right? So I'll be at about 180, so I can almost do it full out, but the mosaic spread's a little high. Maybe I want to drop the divergence. It's going to give me better data, okay? If I go to 220 and I'm right on the edge of using 7, and I'm all the way back at 15, I might be able to go down to 5 millirad, push the detector in a little bit, get better coverage with the detector. The exposure times are a little longer, but the data collection time is not going to be that much different. I'm going to get better data. So as it turns out, the wider the spots are, the more background that's contained within the spots. So the smaller spot profiles, a lot of times you'll just get better data. So it's kind of, you'll learn to play around with this a little bit. So if I put on a crystal and the spots are really close and I'm pulling back and I'm not really getting them resolved, I'll just go to a lower divergence, and that will solve the problem. Okay? Does that sort of make sense? Give you an idea. And when you get in there, start playing with it. What I would suggest doing is you have your sample on, and I've got a picture of this. Put on a collimator with a higher divergence and see what the spots look like, and then put one on with lower divergence and see how that changes. You'll see the heights of the peaks go down, but also how wide or narrow they are will change. Okay? And so this is an example of that. So at the very top, that's 5 millirad, that's 7 millirad. And again, it's a little hard to see, but these are really overlapping down here, where if I go to 5, I'm almost back to baseline. And so that's what you will see if you change divergence. So a lot of times what I've done is I've actually gone to a lower divergence, counted longer, and actually gotten better data at those gray areas where it's in between, where that's optimum for that divergence. Okay, so data collection strategy, we've talked about what you need and what you're shooting for. So, so the thing the program figures out is how to get a complete data set, what multiplicity you want from that data set, and what the total exposure time is going to be for your data set based on the exposure time per frame. So what you see here is that the first thing you do when you get in is it has the unit cell. It's going to have the resolution. You need to put in the resolution, what you think. The program will try to suggest it to you, but you want to put in the resolution you think you want to go for. The program is always going to suggest the lowest possible symmetry. Okay? So inherent to X-ray data is it's centrosymmetric, right? Friedel's law, HKL is equal to H bar, K bar, L bar. So there's a center of symmetry in all data sets. Your crystals will all be non-centrosymmetric, but the data itself has a center of symmetry. So what you can do is set it up as a centrosymmetric point group and collect your data like that. So what that's going to do is, so for monoclinic, I would set it up as 2 upon m, and it's going to treat I plus the same as I minus. So it's going to find one, not necessarily the other, and it's going to say that's a complete data set. Okay, and that's valid. So if you want to collect just a really fast data set, collect it as a centrosymmetric point group. But if the true data is really I plus and I minus separately. So the program will always suggest that you do a non-centrosymmetric point group for whatever point group you've suggested when you've indexed. So where you can go into trouble is this. So say I've got a tetragonal cell. And I don't know if it's high symmetry or low symmetry. So I don't know if it's 4 upon MMM or 4 upon M. So at this point, I have no idea. It's going to be based on the rotational symmetry and how well the reflections merge. So if I set it up to be high symmetry and it's actually low symmetry, I'm going to miss data. And I'm not going to have a complete data set. So the program always sort of defaults to the lowest possible symmetry. So you always see it as, for monoclinic, it'll be chiral 2. For orthorhombic, it'll be 2, 2, 2. It always picks the lowest symmetry. But you can put in any symmetry you want based on that Laue symmetry. So if I know it's tetragonal and it'll suggest chiral 4, but I know it's high symmetry, I'll either put in 422, or if I want a really fast data set, I'll go put 4 upon MMM. And so that's how you put in what the point group symmetry is. Okay, does that make sense? So a lot of people get confused about this as far as, well, I've got protein crystals non-center symmetric. Well, that's true, but the data actually has the center of symmetry. Now, if I were doing a SAD data set, I would want to leave it as non-center symmetric because I'd want to keep I plus and I minus separate because I'd want to measure them equally. So if I set the multiplicity to 10, I'd want I plus measured 10 times, and I'd want I minus 10 times, not I plus measured 20 times and I minus measured once. So if I'm doing a phasing experiment, then I do keep it non-center symmetric. But if I'm doing just a standard data set, you can set it up as a center symmetric data collection, and it will do as fast as possible. Okay? There's other things in here that you might actually find useful and you can try. So you can actually do an already measured. So it'll take a HKL file from a crystal you've already measured on and then try to find the missing data. So if you're doing a room temperature data set and you're doing it for multiple data sets, you can read in an HKL file and it'll look for missing reflections based on the orientation matrix, the cell, and try to find those first. So that might be something to try to work with. Measure from file means that it tries to duplicate data sets. So it tries to take your data and collect it in the same way in a different crystal. That's more of a test, accuracy between crystals. So the first thing we do, okay, we've got the unit cell and we've got the resolution we want. So now we want to set up our data collection. So we put in the crystal detector distance. The program will try to suggest what it should be, but if you've got spots that are overlapping, it'll have a hard time. So put in what you think should be the value. Sometimes it's actually close, but it depends on how much data you get from the indexing. You can do different ways of data collection. I just use the default generic and phi scans, but you can do only generic omega and phi scans. You can do just generic omega scans if you want, and I'll show you what that means when we go in the X-ray lab. You can do Friedel mates on the same image with a kappa goiostat. You can put Friedel mates on the same image. Or you can do inverse beam as well. But because the radiation damage isn't on the same level or as quick as you have the beam lines, these two really don't do a whole lot for you. It's really not, your crystal's not decaying that fast. Next things in here, you always do shutterless mode, so that will always be checked. You want to have this checked, and it should be by default, that the program doesn't allow the goniometer to go right underneath the cold stream. So you don't want to be kappa 0, because what will happen is you'll come in a day and there'll be this giant ice ball sitting on the goniometer because it's not heated. So the program only calculate runs where the goniometer is out from underneath the cold stream. So that does it in the collection strategy, but you may forget sometime. You may leave the goniometer kappa 0, walk away. Even overnight, I've come back and seen a giant ice ball sitting on the goniometer. Don't panic. Just shut the cold stream off and let it warm up. That will, if you try to move it when it's frozen, you'll break one of the drives, primarily the phi drive. But if you just let it warm up, you'll be fine. Okay. But this will help you prevent that. Just kind of keeping that in your mind, and when we go in there, you'll see what I'm talking about, is that you just don't want to leave kappa underneath the cold head for a long time. You can do it for a short amount of time. You can even collect data on a fast data set like that, but you just don't want to do it overnight. Avoid overlaps due to long axis. That's not checked by default, but you can check that, and what that does is what I mentioned, aligns the rotation axis along the long axis, or long axis along the rotation axis, and that helps minimize overlaps. Strict 2 theta efficiencies. That means that I'm not going to swing the detector way out to get the high angle data. So sometimes the most efficient way to get a certain resolution is to swing the detector to a very high 2 theta angle so that you only have half the detector filled with spots. So a lot of programs don't like that. A lot of integration programs don't like to have half the detector empty. So what we do is is fix the edge of the detector at the resolution you want to collect. And so the program won't do that. It will probably take a little longer to do it that way, depending on the resolution you're at. But that forces to have mostly, the diffraction limit at the edge of the detector. And then the multiplicity is something you'll have to consider. So we do something called the 90% rule. So we say that we try to get the same multiplicity as a function of resolution. So it's in bins, it's 90% the same all the way across from low to high. So that's probably the best, most evenly distributed way to do a data collection. But it's also the longest. So if I put in a multiplicity of 4 and I do 90% rule, I'm going to end up with like 8 or 9 multiplicity just because that's what I have to do to get that even distribution. What you can do, and that's fine, you can do it that way, or you can uncheck this and then it just does it based on completion, not on multiplicity. So basically if I do it just on how complete the data set is, I'll end up with about 3 to 5-fold, depending on the symmetry. So that's quicker. So, and when you play with this, you'll see what I mean when we go through the strategy.
So,
yeah.
when you collect SAT data, sulfur SAT data, so in that case, you need higher multiplicity. So in that case, you should uncheck this.
So I would check this, and then set the multiplicity you want. And then it will probably gain that, it will do a better job, and it'll do it evenly across the resolution range. So for your SAT experiments, you're going to be cutting the resolution for substructure determination around 2.5 typically, and go from there. So that's where you really want it evenly distributed and the highest multiplicity, because that's where you're looking for that precision. So I wouldn't use just the completeness in that case. I'd probably use the 90% rule for that. That's going to guarantee you're going to get that to whatever resolution you're using for that. And then put in whatever you want. So if I put in, say, 5, I might see that gives me 10-fold. Oh, I'm good. So just kind of play around with it. It doesn't take a long time to run. But for a SAT data set, I would probably check that and use the 90% rule. And then also non-centrist metric for your point group designation. What it does is then it tells you the runs that you do, how complete the data set is on a run, and how long it's going to take. And you also have graphs up here that show you, here we're saying it's complete all the way to the diffraction limit. Here's the multiplicity going across residual space. So this gives you an idea of how you did. And that's all you need to do. And that does data collection. And then you just put in what rotation angle you want and the frame time. And that's it. So what the program does then is it figures out what runs are necessary for getting those targets we're going after and how long it's going to take. And in here you can do more complicated things. This is more small molecule than protein, but for small molecule what you typically do is wedges of data because you're going at such high resolution. So you might do low, medium, high resolution, and you do them in wedges. And so what you can do is actually change exposure time depending on the data you're going after. So you won't have to expose your low angle as long as you would your high angle. And you can change that, and they'll still scale together well. So if you get into a protein crystal that is really diffracting well, say 1.2 angstroms, but the cell's a little bigger, surprisingly, and you have to pull the detector back, you can actually set this up to collect the low angle data shorter than the high angle data. And then you can also tell it, I want a 4-hour data set. I want it done in 4 hours, and it'll adjust the exposure time to match 4 hours. So just remember that if I say I want a 4-hour data set, it's going to shorten the exposure time to match that amount. And it just tells you when it's going to be done, how long it's going to take data set-wise. And then you can actually look at the runs. So there's prepare, edit. And you actually go in there and actually edit the runs and change them if you wanted to. So if I found, I'm getting too much data, I don't really need that much. Usually the first runs is most of the completeness, and then afterwards you're just filling in what you're missing and then adding multiplicity. So you can actually shorten the other runs if you want to speed up the data set. And you can do that just by changing what the sweep width is. Angular range. And you could actually put your own runs in here and then put apply, and it would tell you how you did. So if I want to do 90 degrees phi scan, how good am I going to do? It'll come back and say, this is how complete it is. And then if you say extend, it'll just fill in what you're missing. So if you have a favorite run you want to use, just a 9-degree phi scan, for instance, but I'm missing some data, let the program fill in behind that. And it's fairly straightforward to do that. Now I can show you how to do that. And that's just what the runs look like, and we'll show that in the X-ray lab. And then once you've got the strategy done, there's a little button that says Apply Strategy down here. You just click it, and it reads in the strategy into the experiment window, and you just hit Go. The program automatically validates the runs, so they're good. Even if you put your own run in here, the program will validate it and say you can or cannot do it. It'll say it's okay or something's wrong, and it'll try to tell you why. So there's a Validate button down here. There's a Resume and Execute. We'll talk about that in the X-ray lab. But it always does a validation regardless. It won't allow you to put in a run that isn't allowed. Okay, so that's the data collection. All we have left is the data reduction. So let's take a quick break, and then we'll go ahead and finish this up. It'll just be about another hour. So now we'll just go through data reduction and evaluation, looking at some of the programs you can use to see what the data quality is. I'll talk a little bit more about that tomorrow. We have a plugin that you can run aimless and pointless through a PROTEUM. So with CCP4 installed, you can actually run those programs to generate an MTZ file. And you can pretty much take an MTZ file into any program you want afterwards. So that's one of the things we did to sort of make it more compatible with going to some of the other software packages that are out there. So you can use our data analysis, or you can certainly take it into other programs. Use Xtriage and Phoenix to look at the data quality. And theirs do a little more extensive statistical look at the data itself than what XPrep does. So it does a lot of twinning checks. They'll look at in the space groups, look a lot more at the rotational symmetry to figure out what the proper space group is. So Pointless, Aimless, and both Xtriage are really good programs. So if you want to do data reduction, then you just go to Reduce Data. So again, the menu items are sort of in the direction of the experiment. So you go from top to bottom, and that goes from the beginning to the end of the experiment. So you have Integrate Images and Scale. Those are the two you will use. Also, Unwarp and Convert is in here. So that's where you would convert frame formats. And we'll talk about that tomorrow. So integration, so basically all integration is I'm predicting where the reflection is on the detector face, and I'm going to that area and I'm integrating under a certain mask. And that's giving me my intensity value for that Bragg reflection. And so that's all integration is. But there are some components to it you have to treat carefully to get accurate measurements of the intensities. First, you have to determine what the background is, and what all integration programs do is they determine local and global background, and they subtract that from the image to improve the signal and noise. You make a mask, so the program automatically generates what's called a pixel mask, and where are the dead areas of the detector. So for a Pilatus that you've seen at the beam lines or a Dectris detector, you'll see all the gaps, and those are dead areas in those detectors, and you have to mask that out. And the reason for that is that the integration program has no idea they're there. I mean, all it's doing is going and predicting where the position of the reflection is and integrating. So if that spot lands on a dead area, it still integrates that spot. It doesn't know that that's a dead area. And so as a result, what will happen is you'll have all these reflections that are nonsense. And so a lot of people say, well, when I scale, it'll just get thrown out. And that's true in most cases, but not in all, because in scaling, sometimes I might have singlets, doublets, or triplets. And so if I only have two reflections, I've got one at 0 and one at 500 counts, I have no idea which is the right. So I'm going to average those together. And I'm going to have an error in my measurement. And so you want to get rid of the dead areas as much as you can. in integration. And so our Saint actually does this automatically and creates a pixel mask for you. You can also generate your own mask. So if you were doing beamline data, for instance, it's really hard to mask out the gaps in a Dectris detector. So I can show you how to generate a mask, and you can just read that in. And then it's the same for every data set you do off that detector. You read in the orientation matrix from your indexing, and that gives you how to predict where the spots are. You determine initial spot shapes. So Saint determines the spot shapes for you. So if you've used Denso or HKL in the past, you know you have to specify what the spots look like as far as shape and size. And Saint, as an XDS, it does that for you. It automatically generates a spot profile based on a bunch of spots in the similar area of reciprocal space. And so it does that. And then in the beginning, what it does is it takes about, I don't know, about 20 or 30 degrees and harvests reflections and updates the orientation matrix. So at first you see it say it's refining the orientation matrix, and it does this between 4 to 8 cycles. And what it's doing is trying to get the best orientation matrix so it can have the most accurate prediction of where the spots are. And you'll see, based on the spots, how they'll change. So it'll show you three-dimensional profiles, and you'll see the spot will be off the box, and then it'll get pulled in. And you'll see the box change as you're refining the spot shape and the orientation matrix. So it does all that automatically. So then you just put in each run you're doing. So say you did a data set and you have 3 different runs. You put all 3 runs into the Sync GUI, and you hit go, and it automatically does all 3, and it uses the orientation matrix on all 3. So you don't have to index each run individually. It will do that automatically. And then at the very end, it will eliminate spot shape correlations that don't match the spot shapes that it's got for a particular reflection. So it tries to kick out outliers. So the GUI is pretty straightforward. So there's a couple buttons up here. You have to, first of all, it reads in the cell for you. And if you had multiple cells here, if you're doing a twin, for instance, you check multiple cells, it would then know it's a twin and treat that accordingly. It just knows that you have a single domain. And so you put in the resolution. Again, it will try to predict, but you put in whatever resolution you want for the integration. Down at the bottom, they have refinement and integration options. I'll show you those in a second. It has, you can read in the frames. Go out in the hard drive and look for them. Or if you're connected to the instrument and you're doing this on the fly, you can just say import like this. And it'll read in those frames. And then at the very end, you have start. So here's the 2 ways to read in runs. So you have find runs, and it'll go out and then look for all the runs with that file name. So remember I said our frames are file name, run number, frame number. And so the program can then easily go out and look to see how many runs are on the hard drive, how many frames are in each run. And you can adjust that to wherever you want. You can read those in. Or you can input them. So I'm connected to this, and I just ran an experiment. This knows what runs I've done. I just say import, and it reads in the runs that I've done.
Your battery's back. This one probably.
Oh,
On slow. Nice guys did.
So like every other integration program, you have refinement and integration options. The refinement options, I really don't play around with much. I'll just talk about what they do. What you'll find in Sling is that the defaults are pretty good. So standard stuff, you won't change anything. You'll just hit go. And it'll do a pretty good job of refinement. But it's for the weaker diffraction or the trickier data sets that you might have to change some of the parameters. So what the program does is it does a least squares fit per frame. So it actually, per frame, it does a quick least squares to try to get the best predicted position. So that you should do automatically. It will start with a box size profile based on your index frames, and it will refine that. So it does a pretty good job of refining the box size as well. So I usually let it do that. The only problem I've ever seen is if you get a really high mosaic spread, and you say you're about over degree 1.2, 1.5 degrees, it might have some problems in that direction trying to pull that box size in. So you can fix the box size if you want to and see if that improves things. Every integration program does a least squares refinement at some point during integration, and that's kind of a throwback to days when we used to shoot things wet. The crystal and the capillaries would actually move as you rotated them. So you could actually, especially if you had a very slippery cryo or solvent that you were using, like MPD, you could actually see the crystal move as you rotated the crystal. So the programs were made to actually stop at some point and update the orientation matrix so you kept predicting the positions correctly. Now everything's frozen for the most part, so you don't have to worry about that, but we still do that to try to improve how accurate the predictions are based on the observed positions. So every 50 or so frames, you have a lot of reflections at this point, we'll stop, do a quick least squares refinement, and then move on. So say on your system we'll run about 3 or 4 frames per second. So the integration's pretty fast, even on the computer you have. So it's pretty easy to refine and then go back and change something if you want to. That all depends on the number of spots. So you have a really large unit cell, of course, that will slow things down. So I usually start at 50, and that's usually enough, but there are times, say sometimes what will happen if you have a really large crystal and a large loop, and you've probably seen this beamlines, as you rotate, the stream of the cold stream can affect the position of the crystal. Randy Alcar at SBC did a nice poster years ago at ACA where he saw that when you got the loop perpendicular to the flow of the stream, the crystal would actually flicker and you could see it moving. And this affects the positions, obviously, of the spots. And so that's an error that you incorporate in your data that you can't remove, or is difficult to remove. And so you will see cases where sometimes the predictions kind of vary a little bit. And a lot of that's due to if I can't resolve the spots, if I'm getting to an orientation where they're starting to overlap. And so you can do this a little more frequently. Sometimes it helps to do the least squares refinement a little more frequently, but usually 50 helps. 50 is fine. And then because we have so many reflections, because we're doing so many frames, we can refine all the different parameters. So it refines all the different hardware parameters. At the very end, it does a global refinement. So this is a three-dimensional profile fitting. So what it does is that it doesn't treat the data in a two-dimensional sense like Denso does or MOSFilm does. So Denso and MOSFilm, the two-dimensional approach says each frame is independent. And so I look at one frame, I integrate, and then I look at the next frame to see if it's the same reflection or a different reflection. So I treat each frame as a separate piece of information. So at the very end, then what I've got to do is I've got partial reflections, right? So not every reflection is complete on one image. They spill over to the next image. So I've got to determine if the spot's the same, I've got to sum them together. And you'll see at the end of Denso or HKL, that's why HKL has all these raw files they have for each frame. And then at the end, they do a post-refinement, and they sum and merge reflections together. MOSFilm does it automatically. You don't see it, but Denso does it like that. So that's the two-dimensional approach. And that works really good if the rotation's really wide, like a degree or more, because you'll have fully recorded reflections within that degree. And you'll have most of that rotation will be reflection in that case. But the difference between fine slicing and wide slicing, one of the advantages is if I do a half degree or a degree rotation and the rocking curve or the start or finish of the spot is a half degree, then two-dimensionally I include all that background into that reflection, right? So if my reflection only goes half degree and I do a degree rotation, then half of my intensity that I'm putting in is background. So that's why people start going to fine slicing, is because you only integrate the actual spot rather than just the area around the spot. And that should improve the consistency in your data set, because your background can vary pretty widely as you rotate. So that was the whole idea, one of the ideas of going to fine slicing. So, but that's hard to do in a two-dimensional sense. That's why programs like XDS and Saint were developed to do fine slicing, because they do a true three-dimensional profile fit. They don't treat each frame as a separate piece of data. They treat it as an angular range. And so you're not summing reflections. You're only putting a mask around that reflection, and you're integrating. And so it does a better job at handling very fine slicing, because if you do a 0.1 degree rotation, for instance, there are no fully recorded reflections on that image. And so it's difficult for a two-dimensional approach to deal with that. And so the three-dimensional approach that Saint and XDS do are geared towards fine slicing. And it does a really good job with that. So some of the integration options that you might play around with can affect the data in cases where you're getting not the results that you expect. So first of all, three-dimensional approaches generate a model profile for you. So what it does is it looks in an area of reciprocal space around the reflection that you're integrating, and it builds a model profile. So what does this reflection look like? When does it start? What is its shape? And then it uses that profile over all the spots. And then instead of just integrating over an area, it actually applies that profile to each spot. And that only integrates underneath the curve. Okay? And so what we do is, there's two ways of doing that. You can either blend all the regions of the detector into one profile. So have one profile over the whole detector region. And that works best when you have a weak scatter, because you only have very strong reflections on only certain parts of the detector. If you have a medium or strong scatter, the best way to do it is to break up the detector in different areas. So this is the old XDS approach. So it's one region in the middle and then 8 around the outside. So you've probably seen on your images before that they look like ellipsoids, and they're going one direction on one side of the detector, and they're going in a different direction on the other side. And so the idea is that if I only model or make model profiles for specific regions, it's a better fit for that area of the detector. And so that's the idea of having it broke up into different regions. But what I've found is that if you have strong enough reflections over the whole detector face, then that usually works the best to have multiple profiles. If you don't, and it's a weaker scatter, then blending is probably better. And you can do that just by checking or unchecking the box. So check it to blend, check it to unblend. And the integration is fast enough where you can just try both and see what will give you the best result. Sometimes they're pretty much the same. Sometimes one will do considerably better than the other. So that's the model profiles. So the other thing to do is to look at how you generate the model profiles. So we basically generate them by taking strong reflections, because those are the ones that are most accurate. So in other words, 10 sigma. We use a 10 sigma cutoff by default. So any reflection that's above 10x above the background we'll use, and we'll sum those together to make our model profile. If the data is weaker, you can reduce that. If the program comes back and says, I'm just not finding enough strong reflections to make the profiles, you can drop this down to 7 or 5. But I've found that if you go below 5, it really doesn't help. That if the data is that weak, 5 is going to be just as good as 3 or 2. So usually 10 works really well, unless you have something that's really weakly scattering, and then I might try 5 or 7. The next thing is how much you cut off on the tails. So in the old CCD detectors, they used fiber optic tapers. And so they were blackened out to keep light from spilling over and sort of guide light in a specific pattern. But what would happen, it wasn't 100% efficient. So what you would see is on the reflections, you'd have tails. So you'd see a Gaussian curve for the most part, but it would be these long tails. And so what most of the programs did was said, okay, let's just cut the tails off at the bottom, and that will make our data be more internally consistent. So there's a sort of a throwback to the CCDs that used to use large tapers, where you can actually cut off the bottom part of the reflection. Your detector doesn't have a large fiber optic taper, and so you can actually set this to 2% or even 0 for the data you do. 5 is the default, and we can change that if you guys want to play around with that. But all these defaults can be changed as well. But that's just what that throws back to. The intensity, the signal noise for least squares refinement deals with the profiles. So as it turns out, the profiles are based on your low-angle data, right? Those are the strongest. And so the profiles look most like the low-angle reflections then, which makes sense because that's how they're made. So at low angle, for the strong reflections, I do a simple summation. All I do is take the profile, I put it where I think the spot is, and I sum underneath the curve, and that's it. And that works really well for the low angle data. But the high angle data are going to be more diffuse and lower peak heights. And so what the program does is it refines the profile against the high angle data to give you a better fit. And so that actually helps the data considerably on the weekend. So the program will say anything lower than 8 sigma, I'm going to do a least squares refinement to make the profile better. Anything stronger than 8 sigma, I'm just going to do a simple summation. And that 8 sigma is kind of by trial and error. That we found that works really well. I have found at times, though, that if I'm having trouble with the low angle data, I may extend this to, say, 20. Just do a least squares refinement on all the data, and it will improve things sometimes. So it's something to look at if the low angle data is a little higher than you think. And the last one is the profile of the HCal of the box that you're doing for your integration. So this is 2n plus 1, so that's going to be 9. So you're going to see a 9 by 9 box in the profile fitting. If you go to really fine slicing, it's nice to increase that to sort of break it up into finer slicing, sort of match the rotation. So at 0.5, 444 is fine. But if I go down to 0.2 or even 0.1, I might increase that to 888 just to make the box more finely sliced to match the rotation I'm doing. So when you're doing data collection, you'll see beamline data talk about doing these really fine slicing. I even got one data set from Swiss Light Source that was 0.025 rotations, 16,000 frames. And at the beamlines, there's a paper that Dectris put out in Acticris which talk about how that can improve the data. But that's geared towards a beamline where the beam is parallel and very small, so your spots are very small. Here you're working with a focusing optic and the beam's much bigger, and so going to the really fine slicing is not really going to improve things much on the home lab. So going below 0.2 degree rotations is probably not going to gain you anything. You can try it and prove to yourself, but I would say it's just going to generate a lot of data and it's not really going to improve much. But between 2 and 5, 0.2 and 0.5, that can be a place where you find a sweet spot. Especially with a long axis, I would go down to a smaller rotation. That will help you resolve the spots. This makes a big difference, and the way you determine the background, and I would suggest trying either method to see what gives you the best results. So we do 2 different methods of determining the local background around a reflection. Remember I said what you do is you determine the local background and you subtract it from the images to give you a better signal of noise with your reflection. And we didn't even realize it would make that much of a difference, but in cases I've seen, if I've got an R merge of R measure of 12%, and I do another one of the other method, it might drop to 8%. That's how much of a difference it can make just by how you subtract the background. So something like lysozyme, not going to make any difference, right? The reflections are so strong, it's not going to matter. But for things that are more weakly scattering, this is going to have a huge impact on the quality of the data. So the recurrence method is that I look at the same pixel over an angular range and I average that pixel to give me my background counts. So you would think that would give you the best estimate of what the local background is. But if the background's highly varying, if I've got ice diffraction or I'm in the diffuse solvent area and the backgrounds, or I have diffuse scatter in general, that can cause problems because as I rotate, the background's changing too much. So there's 2 methods. Recurrence method, which is looking at an angular range of the pixel and doing an average, or the best planes, which is just plotting out the local per frame. That's what Denso does, that's what XDS does. So these 2 methods are quite different as far as the results they can give. And I would always check to see which gives you the best result. I've just been playing around with this the last couple of years and had noticed that it can have a huge impact on just the internal agreement of the data. Image queue is something that everybody's always confused about, and we should make this a little easier to understand. But how how three-dimensional works is that I define a rotation, and I say the spot, the diffraction, must start and stop within that rotation to be a fully recorded reflection. So I may make my angular range, say, 10 degrees. And I say anything that's wider than 10 degrees I throw out because it's too wide. And you might say, well, that doesn't sound right. What reflection would be 10 degrees wide? I mean, most of the mosaic spread, are less than a degree. As it turns out, as you get along the rotation axis, as you rotate, the spots stay in the reflecting conditions much longer than you normally would, just based on the geometry of the experiment. It's called the Lorentz region. And so the spots can be as wide as 15 degrees. So, and you look at them, you'll see it on the screen, if you look at the rocking curves, or where the starts and stops, and you're along the rotation axis, the spots are just really wide. If you go to the same spot 9 degrees away, it's under a degree. So if you think about that, if I take the same reflection, I'm trying to scale it, and this is 15 degrees wide, and this is only a degree wide, they're not going to scale very well, right? Because one's going to have a huge amount of background in it compared to the other. And so we try to throw some of those reflections out. And all programs do this. And that's why at the beam lines, they put when you have a single spindle, they put the beam stop along the spindle rotation, because you're going to throw that data out anyway, so you don't have to worry about the beam stop shadow. And so when you see at the beam lines, you have a single spindle, the beam stop is always along the rotation. And so you can do this by adjusting the image queue. So this is 2n plus 1. So if I have 7 in there, that's 15 frames. So I multiply the number of frames by the rotation width, and that's my queue. So if I have 15 frames, I'm doing a 0.5 degree rotation, that's 7.5 degrees. That's telling me that a reflection has to start and stop within 7.5 degrees for me to accept it. Otherwise, I'm going to reject it. And you'll see this little cone where I'm throwing out reflections, just because they're too wide. So you could increase or decrease that to throw out more or less data. So if I have a high multiplicity, I can make that really small and throw out more data, because I don't care, because I've got more data collected. But if I'm getting just a complete data set and I want completeness and I'm missing some reflections, I'll increase that to bring in more reflections. Because even though they're not accurately measured, they're probably better than no reflection there at all, because that induces truncation errors in the Fouriers. So you kind of can adjust that to give you a sort of a baseline to go by. For a half-degree rotation, I do between 7 and 10, because that gives me 15 to 21 frames. So it's on the order of 7 to 10 degrees in my queue. If you do the 0.3 degree rotation, you have to increase that, because it's the number of frames times the rotation width. So if I do 0.3, then I'll go up to 15 or 16. That'll give me about the same queue. Okay? So if I want more reflections, I increase this number. If I want less, I make it smaller. Does that make sense? And if you think about it, it's just this. It's a number of frames that I'm throwing into my queue. And I'm saying a reflection has to start and stop within this range. If it's longer than this, then I throw it out because it's too wide. Some other things in here that you won't play with. So we have a fewer and more options. So we try to limit the number of options we're throwing at you all at once. So if you hit the more options, you have things active mask. You can read in your own active mask. This is what I do for synchrotron data when I take a mask to get rid of the gaps. You can do a wide narrow frame algorithm. So if you were doing a degree rotation for some reason, the fine slicing might not work as well. So we have a different algorithm in that does more of a two-dimensional approach. So you can try that. If you've got a degree rotation or higher, I would definitely try the wide frame algorithm instead. And then there's a bunch of stuff related to twinning that you can play around with if you ever get in that condition, and we can help you with that. And then what it does is it makes all these plots. So it shows you what's going on in the data set. So these are the 4 that we think give you the most information. This is the correlation coefficient, and that's how closely does the profiles match your actual spots. And what you should see is this should be pretty consistent. It'll vary based on the intensity, because how well the spots match to the profiles will be based on how strong the spots are. The weaker ones won't match as well. The stronger ones will. So for instance, if I'm integrating too far out in resolution, this will be artificially low because the data is too weak. I'm just essentially integrating noise. So this will vary up and down a little bit based on the intensity of the reflections, but should stay consistent. If I were to see this drop and come back up, something's wrong in that frame. And if I put the cursor over the little dots, those are each frame, it'll tell me what frame number is, and I'll go and look. If I see this come over here, I just saw this on a data set somebody sent me. The crystal actually moved during the data set. So it got into a position where the magnet wasn't strong enough to keep it in place, and the cold stream hit it and it moved. And you could come up here and you can see the correlations, and they just all of a sudden just dropped. And that's telling me that something's changed, right? The orientation of the crystal's changed. And so, and the program couldn't, so far, the program couldn't pull it back in. So that's kind of stuff that these will tell you is if you look for the abnormal, but there will be variations in these. This is the I over sigma I and the average intensity as a function of frame, and this will tell you kind of what's happening as you rotate the crystal. So if my crystal is much bigger than my beam, the volume will change as I rotate. So you'll see sort of a sine wave. So the intensities will go up and down based on how much of the crystal's in the beam at a given time. And so that's what the scaling's taking out. That's one, if I had a perfectly spherical crystal and I had it fully bathed in the beam, I would never have to scale my data because there'd be the same volume in that data. And so with the ILID crystal we use as a test crystal, we typically don't scale the data to see how well the internal consistency is. This is the profile. This is what you want to see. That gives you an active three-dimensional profile. It shows you the box, and you'd want to see the green inside the box. You don't want to see the profile on the edge. A lot of times you'll see twins where you'll start to see a second peak coming in and things like that. That's the kind of stuff you want to look for. But for the most part, you want the peaks centered within the box. And there's a listing file that shows the numerical value of all these graphs that I'll show you as well. And then this one, it's just it's kind of a chi-squareds plot. This is just the differences between the predicted and real positions, centroids. And what you want to see here is it'll vary. These are in errors in pixels, and it'll vary between 0.05 to 0.2. But what you don't want to see is one of the axes going off on its own. That means that the program's struggling trying to figure out where the centroids are for those peaks. And there's all kinds of other plots you can show if you want to. And here's a listing file, and I can show you one of those if you're interested. It's just got all the numerical numbers from just the graphs that you're looking at. It's a place to look, and I can show you things in the listing file, places you want to look to see how the integration has gone. So what I will give you as a cheat sheet is I've got a PDF where I put out what all the output is. So when you do data reduction, integration, and scaling, it creates a work directory, a subfolder in your frames directory where it puts all the data reduction files. So like every other program, it's sometimes hard to figure out what file is what. So what I did was make a sheet that tells you what the extensions are, what's in the files, and the short description of them, so that you can just look at this and say, okay, my raw files are my raw, unscaled intensities that come out of my integration program. My _ls file are my log files for my scaling. For each run, it gives a list file, and then at the very end, it creates a merged file that has statistics from all the runs. P4P file is my matrix file. That's my orientation matrix. So there's a file, if I wanted to take an old data set, for instance, and I wanted to create a new entry and look at the data again, I can read in my P4P file, and it's got my old orientation matrix, what I did before. Active mask, you can look at the active mask, and I tell you what the name of it is, and then the chart file. That it saves all the charts, and you can reload those in if you want to look at them again. The thing you're really interested in is the raw file. That's what you're going to scale for your data. And then the listing file, because you can look in there and see what's in there, what it's telling you. And what I'll do is I'll make a little guide for you guys for what I think to look for in the listing file. So there's a couple things in the listing file that gives you some information on how things are going. We actually show the amount of overlap in the spots, and that tells you if I'm at the right crystal detector distance. If I go in there and I see the spots are overlapping by 50%, my next crystal, I'm going to want to pull the detector back or change the divergence to get better scaling. You can look to see if spots are at the saturating detector. You probably won't saturate the detector very often in this, because I get a feeling most of your crystals don't diffract that well. But if you had something really strongly diffracting on this system, you have to worry about overloads. And so you might have to do a low angle pass. Depending on your zDNA crystals, that's going to blast the detector. And there are attenuators you can put in as well. There's an attenuator in the shutter, and then there's a manual attenuator. So you could actually attenuate the beam quite a bit if you had to. There's things in the log file that you can look at that give you some feedback about how the integration goes. So I'll give you guys just a quick cheat sheet on that. So then, once we have the raw files, we can go on to scaling. So the idea of the scaling, as we talked about before, we're just trying to put it on make the data internally consistent. We want it on a global scale, and that's what the whole thing is. And then we want to create some standard deviations that model the spread of the reflections. So when you scale, what you do is you have a reflection, and for that reflection, I have multiple observations typically. So I look at the multiple observations and I find the mean of those observations, and that's my intensity. But the observations aren't all equal, and so there'll be a histogram basically of those, or it's a Gaussian curve of those reflections, right? So I'll have some reflections that are pretty close to the mean, and other ones that are farther out. And so the wider the spread, the less certainty I have in what that true intensity is. And so that should be reflected in the standard deviation. So when these programs, ScalePack does the same thing. When we do what we call an error model, is it's calculating what the spread of the reflections are and relating that to a standard deviation. So something that has a really high spread has a high standard deviation or uncertainty in what the intensity is. Okay? So when you see somebody talk about error model, they're doing a chi-squared analysis of what the spread of the reflections are and calculating an uncertainty based on that are away from Poisson statistics, or just random errors. And so then we're trying to deal with all the systematic errors. We're trying to deal with crystal volume changing. We're trying to deal with radiation decay or crystal decomposition. Intensive variation is not that big of a deal on your system, but basically it's going to be, and absorption can have an effect too, right? So if I have a very fat plate, a very thin plate, as I rotate it, the absorption is much different in one direction than the other. And so I should correct for that. Even though I have nothing, for the most part, but light atoms in my structure, I still have to correct for that. Okay, so scaling is really straightforward because it's more black box than any of the other programs we have. And this is written by George Sheldrick. It's a program called SATABS. And basically, you read in the raw files. So what the program does is you just click the browser button and it goes out and shows you all the raw files. You just highlight one raw file of any data set and it'll automatically read in the other raw files. And so this allows you to read in the raw data that you have from your integration. And then if you say you have three, and this will happen, you'll have, say, 3 or 4 runs, and one run just doesn't integrate well. It's the orientation. It's, it just for whatever reason, it just not a good orientation of the crystal. You can throw out that run just by unchecking the run and not use it in the scaling. And most of the time you'll have enough multiplicity where it won't matter. You can be a little more selective. That's why it always helps to go a little higher in multiplicity. The other thing is the point group. So a lot of people were confused that they always, it's back to the data collection idea, is that protein crystals are non-centrometric, but X-ray data is. And so when you scale, you should choose a centrosymmetric point group. So I plus and I minus are essentially the same based on Friedau's law. Even though you have a non-centrosymmetric space group, the point group symmetry is centrosymmetric. And so you should treat it as such. So when I scale an orthorhombic crystal, it's always MMM, not 222, because it's a protein crystal. Okay? You can, in cases of phasing, SAD or MAD data, for instance, you might want to keep I plus and I separate because you're looking for that difference. Then you would select a non-centrosymmetric point group. So for orthorhombic, if I want to do a SAD experiment and want to keep I plus and I minus separate, I would select 222 as the point group symmetry. And so then I plus and I minus are separate reflections. But for everything else, it should be MMM is what I'm scaling to. And I asked George, because I thought with sulfur, because there's a very weak signal with sulfur, that you would be better off separating I plus and I minus when you did scaling. He said, unless you have high multiplicity, you're better off getting the accurate value of the intensity by merging everything together than trying to separate it and try to find that small difference. So even with sulfur SAD phasing, for instance, unless I've got a high multiplicity of 15 or 20, then you're better off keeping it all together when you scale it. So you can actually change it by changing, there's two buttons. There's, it says log group and point group. If I change the point group to non-centrosymmetric, then it will keep I plus and I minus separate. Normally I just set the log group to whatever log group it is, centrosymmetric-wise, for that symmetry. So the scaling's only based on rotational symmetry, not translational. So it's all the point group symmetry, all the rotation axes in your cell. Translational comes later. And so it will assign names for you, but you can change those if you want. So if you hit the advanced setup down at the bottom, it gives you a way to change names if you really wanted to. You don't have to, but you can. The one thing it does do in here that some of the programs have gone to now is a zero dose correction. And this was found, I think, at the Swiss Light Source back in the 2000s, where they looked at reflections, same reflection collected as a function of time. And they found that there was almost a linear decay in the intensity. And you could apply a correction to that and scale up the reflections collected later and improve the data. And it's called a zero dose correction, applying a scale factor to zero dose. And they found, there was a paper in ActiCRIS where they found that they actually were able to do a SAD structure they couldn't before by applying this correction. And the problem is that unless you have a lot of data, it's really hard to get an accurate measure of what the scale factor should be, right? So if I only have 2 reflections, I have 2 points, it's not really telling me much about how the decay is as a function of time. And so if you have a high enough multiplicity, that might actually help on some level. I talked to Elsbeth Garman a couple years ago, and she said it wasn't perfect, but it's better than nothing sometimes. And so if you have beamline data primarily, it's something to try. For your in-house stuff, I don't know if it's really going to help much unless you're doing a really long data set. And you're seeing a lot of decay as a function of time. But it's something to try. There's a linear and a quadratic. I wouldn't use a quadratic. I don't think it works. So just the linear function is something to try. I guess people are working on different ways of dealing with this. It's just it isn't trivial to figure out what how to model that decay. Then what you do first of all is you calculate what the scale factors are for each frame. So what the program does is it comes in and shows you the multiplicity as a function of the number of groups. So how many groups have a multiplicity of 4? How many reflections have a multiplicity of 5? And it kind of gives you the distribution of multiplicity as a function of each observation. And down at the bottom is just giving you information about the data set. And then how strong is it? What's the signal noises? What's the histogram for that? So then what the program does is basically find the scale factors, and you hit refine, and we do about 50 cycles, and it's actually pretty fast. And then the program gives you some valuable information about the data set, how precise the data set is. So the first graph is the weight. So all scaling programs do this. They look at a set of observations for a reflection, and they downweight the outliers, or the reflections that are near being outliers. So the farther a reflection gets away from the mean, it downweights its contribution. So what you're saying is the ones that are just questionable, I'm going to keep those, but their contribution to the overall mean is downweighted. So that's the mean weight for an observation, and ideally it would be 1, right? All the reflections are weighted the same. The lower this is, the less precise your data is, and it's giving you information about how good the data set is. So if you're up at 90%, that's pretty good, right? Your data is going to look pretty good. If I'm down at 60%, something's wrong. And that's telling me that the reflections are not very precise, and they're not merging well. And if I go to look at the next step, which is applying the error model, I'm going to be throwing out 20% of my data. So you can't do anything about this, but it's giving you some idea about the precision, internal precision of your data set. So the higher the mean weight, the better off you are going to be. You'll see that. You'll see some data sets that have a really high precision, but the R factor is still 12%. Well, that's just because it's a weak scatterer, right? So the data's consistent, it's just the crystal doesn't scatter that well, and you're pushing the diffraction limit. So you can have a high mean weight or a high precision and still have data that's doesn't look optimum. It's not going to be 3% for our measure. The other plots are your absorption correction. So they have light blue and dark blue. One is before and after an absorption correction. So what the program does is the multi-scan approach. So it says, okay, I've got different scans or different orientation of the crystal. I look at the same reflection in one orientation and then a reflection in a different orientation. How do they agree? And so what I can do is build up a spherical harmonics model of what the crystal shape is. Bob Blessing developed this back in the 90s I think on a program called DEER. So basically, I look at the same reflection collected in a lot of different orientations, and I say the crystal is shaped like this. As a result, the intensities change because of the shape of the crystal, and I apply a correction based on that. And that's the absorption correction that almost every program uses now. So it uses a spherical harmonics approach to model the crystal to adjust for absorption in the sample. And they have some options here. It has weak, medium, and strong. And that's just the order of spherical harmonics you're using. Medium works for just about everything, so you really don't have to change that. The only thing I will change in this is the restraints on the scale factor. So George puts a pretty strong restraint from frame to frame, saying that the scale factor should be pretty similar locally. Sometimes I will let that go, so the default value is 0.005. It's the idea that you don't overscale your data. You're not changing the intensity values just to make the data consistently look better. So you can let that go a little bit. I'll go to 0.01, and sometimes that improves things on data sets that aren't scaling so well. Then the next step is the error model. I'm going to calculate based on that chi-squared model. So that basically tries to, as I mentioned before, tries to represent reflections that have a wider spread in their observations to a higher standard deviation, or have the standard deviation match what the spread is. And so this is very similar to ScalePack. It uses the same chi-squared analysis. But where ScalePack allows you to adjust the weights as a function of resolution, George tells you that you don't know how to do that, and he's going to force everything to be as chi-squared of 1. And so you can't adjust the weights like you can in ScalePack. So if you know how to adjust the weights, you can actually improve things. If you don't know how to adjust the weights, you can actually make things really bad. So basically, he's telling you you don't know how to do it, he's going to do it for you. And it does a pretty good job of determining the error model. And so when you do this, then what it does is it gives you an analysis of what the R factor is and how many spots you're rejecting. So basically, you have some outliers, right? So you're going to reject anywhere from 0.5% typically to 2% of your data, because there are reflections that just don't agree. But you can always make the statistics look better if I throw out 10% of the data, but you're just biasing your data. So you have to sort of balance how much you're rejecting. And so that affects your error model. So the one thing I can do is there's a signal noise adjustment you can make on here. It's set to 4. It's the difference in mean intensity and observed intensity divided by the mean intensity. And that means that the bigger the difference, so if I increase this number to 4 to 5, I throw out less reflections. If I decrease the number, go from 4 to 3, I throw out more reflections. And you'll see that in the data. You'll see the number of rejections. How does that change my error model? Well, if I throw out reflections, it's going to change my error model, right? So if I have 5 reflections and I have a certain spread and I throw out 2, it's going to change the spread of my reflections, so that'll change the standard deviation. So you can adjust the error model by rejecting more or less data, but you probably should keep it within a certain restricted range. And that's it. So there's only a couple things you can change in the scaling. It's pretty much going to do what it does. It's more black box, so it's basically most of the time you're just going to hit finish and go through the very end. You can go step by step, in the same fashion you can with the indexing, or you can just hit finish and go to the very end. But there are a couple things to look at. So one of the things I always look at is it's the scale variations. This tells you the scale factors change as a function of time, or frame as you're rotating, and how they change from frame to frame. And this can give you an idea of the quality, internal quality of the data set. So here, this is pretty normal, right? You get fluctuations from frame to frame. There's a little pop there, but that's pretty good. And you can see that's because the scale variations as I rotate are pretty consistent. That means the crystal is about the same size as the beam. What you will see, though, is this can vary at times dramatically. And so we just had a small molecule, somebody sent me some data from a small molecule, and he was all concerned because the scale variations were off the map. I mean, they were just almost vertical. And it's because he had a 600 micron crystal and he's dealing with an 80 micron beam. And so the scaling will try to take that out, and he actually got an overall R measure for the complete data set of like 6% from that, or 5%, which was great, considering what he was trying to do. So the scaling does a pretty good job. But it gives you some idea of what's going on in data set. But this is what I really look at. If I'm coming down here and this jumps significantly, I will truncate that data if I can. So something's wrong in this run. So if I'm at 5% and I go up, all of a sudden I go up to 15%, something's not right with that data. And you should seriously, if you can, seriously think about eliminating that. Sometimes you can, it's just the crystal and the orientation. And maybe you're getting overlap in that direction, and that's what's causing the data internal consistency to be worse. But that's something that I definitely look at this every time to see if I should truncate it. And on synchrotron data, you'll see that all of a sudden the R factors will just drop straight down, and the scale factors will go from low to high because of the decay in the data. And you'll see that in the scaling factors. And then also these are the chi-squareds that shows you the plot, showing you how the chi-squared analysis go. This is an instance, we show you the outliers, potential outliers. This is water ice rings. That's what it looks like to the scaling program. It's saying, okay, some of these reflections are too hot, some are too cold, and I'm potentially rejecting those because of that. And that's what you'll see in the scaling. If you've got an ice ring in your data, the program will start throwing out some of those reflections because it has a hard time scaling those, merging those together. It just gives you some information. And then there's two files that are written out. Your HKL file is your scaled unmerged data, and that's what your final data is out of PROTEUM. And then there's a listing file, a log file. So this is what you go on to the next step at. XPrep, I'll talk about really quickly, and that's just a data analysis tool like pointless, aimless, and extraage, as I was mentioning before. It tries to determine the metric symmetry for you, and then looks at the translational symmetry to see if it can determine what the space group is, based on the systematic absences for that particular point group. We have a GUI called Space Groups and Statistics that does a really quick and dirty analysis. So basically it reads all the information in for you. It will then look for higher symmetry in the cell. So it will actually go to look, if you put in a primitive cell, it will look for absences as a body-centered or side-centered. And if it finds it, it will come back and say, I really think this is a C-centered cell. And it will try to hear this was a C-centered cell, I think. Oh, this is actually a rhombohedral cell. So it will try to tell you is there higher metric symmetry based on the Bravais lattice. And it shows all the systematic absences. So it shows you what the absences would be for that Bravais lattice. And are they strong? Are any of them over 3 sigma? And what is the average intensity? And that's how it determines from the systematic absences what the true symmetry is. That's how all programs do it. Then you're looking for the translational symmetry. So what it does is it takes a point group, you tell it, and it looks for possible translational symmetry, screw axes. So if it's tetragonal, for instance, you've got a potential 4-fold screw and a 2-fold screw. And so it will show you the number of potential absences, their intensities, and are there any over 3 sigma? And that's what the program uses. So when the data is really weak, it says, it must be a screw axis. I'm going to tell you that this is the space group. And that's how all the programs do it. So pointless, aimless, X triage, they first look at rotational symmetry. Does it match to the point group you're telling it? So in other words, the best way to tell between low symmetry and high symmetry tetragonal is to scale it. If it scales well in one and not the other, that means it's probably low symmetry. If the scaling's pretty similar, that means it's probably high symmetry. And the same thing for the systematic absences. For translational symmetry, you have reflections that are systematically absent based on that symmetry. And so that's how the programs decide whether you have a screw axis or not. So is it P4 or P41? And that's based on those absences. And that tells you, it kind of shows you what if there are absences, and goes by that. So it tries to tell you what the true space group is.
So is there any cutoff for that systematic absences? Is there any like threshold value?
Yeah, so there are built-in thresholds to XPrep that you can change if you want to, but for the most part they work pretty well for the defaults. So how it turns out is most of the time you'll see, if there's some variation, you'll see the average intensity, say, at 10, and the rest of the reflections are 400. And so there's usually a big difference between the systematic absence and not. So the threshold's not as important. Where it gets more important is if you have some sort of overlap. So you have twinning, satellite crystals, then it kind of screws things up a little bit, and the statistics aren't normal. And then you can adjust the thresholds if you want to try to represent that more. But at that point, you can see them visually, and you can say to yourself, I think that's really P41 instead of P4, even though it doesn't look, it looks like there's something going on. And one of the twinning checks he does is the E squared minus 1 values. So the normalized structure factor squared minus 1. And what that tells you is it gives you the distribution of intensity. So regardless of whether your crystal is centrosymmetric or non-centrosymmetric, the distribution is the same regardless of the crystal form. So it's always 0.9, I think it's 0.97 for centrosymmetric, 0.74 for non-centrosymmetric. Doesn't matter what crystal form it is. If it's centrosymmetric, it's this. If it's non-centrosymmetric, it's that. And it's a distribution of intensities. So the higher that number, the more stronger versus weak you have, right? So a twin will screw that up. So if I have twinning and I have overlaps, it screws up and flattens out the distribution. So that's a warning flag. If you see the E squared minus 1 values much different from what's predicted, it'll come back and say, you better check this. And so those are things in the programs. That's what the other programs use for twinning checks. There's other tests, L test and other tests that are used as well. The Britton test.
Yeah, because once I encountered, you have a needle-like crystal, and all overlapping together. It was a cluster. So what I did, I just focused at a point where all the clusters were together. Those needles. And so that kind of data can be resolved through this?
Yeah. Yeah, it's, like I said, they'll show you the systematic absences if you're at that stage. And then you can make the judgment on your own whether there's really translational symmetry there or not, based on how the mean intensity and the strength of those, based on reflections that aren't supposed to be weak, that are not absent. And so you can kind of get an idea. In the case like that where you were unsure, you would, if you're doing molecular replacement, for instance, you'd try both. So you'd try multiple space groups to see what gave you the answer. But most of the time it's pretty obvious if there's something there. If you have enough observations if you only have a couple axial reflections as you measure it, it's a lot harder. But if you have, say, 20 or 30, then you can make a better assessment of whether it's really there or not. Whether the program does or not, it doesn't matter. It's still showing you what it's basing it on. And then at the very end, it gives you just the R merge, just the statistics, and that gives you a quick look at what the internal consistency is. To get the other statistics, I would go through pointless or aimless or X triage. It gives you CC1/2 in a table. It will give you R measure. That's the stuff you'll need for submission. So that's what I would use for that point. XPrep is good for just giving you a quick look at how well the data merges. This is for pointless and aimless. This is how you would set it up. You put it in the bnconfig file to just tell where CCP4 is, the path of CCP4. And what we did was we just simply put in a plugin, a GUI for it, And basically, it'll read in the HKL file. You tell it, if you put in a space group, it won't determine the space group. If you put unknown, it will allow pointless to determine the space group. So you can decide if you want the program to do it. Sometimes pointless will select something when it looks to be a certain symmetry and it's really not that space group. So you can tell it not to do that. And what's nice about this, we made this configurably. You can configure them. So you can type in your own keywords and run the program. So this is actually editable. So these are set up automatically for you, but if you know the programs and you can put your own keyword in, it'll run with that. And then you just hit go, and it calculates both pointless and aimless and gives you the output. You can also, there's flags for doing an R-free subset. And doing it unmerged, which is what I always do. I write them out unmerged because both, if you go into Phoenix, you want it unmerged anyway. And if you go into CCP4, then you can run truncate and generate, scale up the negative reflections. So we put this in there so you can write out an MTZ file. And that was one of the main reasons. Because most people don't like to write out binary files because MTZ format changes, and so it's hard to keep up with what they do. So this is a quick and dirty way of doing it. Tomorrow I'll show you how to convert just an HKL file from SATAPs into the other formats as well. But this is the fastest way to do it. And then it writes out files. It writes out the log file. It writes out merged and unmerged files for you, and then puts them in the names so you know what's an unmerged file. And so those MTZ files work both in CCP4 and Phoenix. That's it. So lots of information. Like I said, you're not going to pick up a lot of this, but at least it kind of gives you just a background on how the software is laid out and what it can do. And then we can work remotely to go through some of this, and we'll learn a little bit more this afternoon working on systems. And then tomorrow, if you're interested, I've got some examples of RLAT. We'll go through data conversion, frame format conversions. Converting HKL files, and then if you're interested, I've got examples of sulfur SAT phasing that you can do with the program. We have GUIs for that. And also an example of a twin we did that I can show you how you would separate it in RLAT and how you would go forward with that. So, okay?